Uh, Hopefully everybody's in. Before we launch into the seminar today, short course seminar today, proper, I'm gonna give a couple minutes just for y'all to fill out the poll that should be on the landing page right now, just to see where you guys are at in terms of the courses that you have attended or are planning to attend, just so we can have a little bit of a reference point for where you guys are at. All right, I'm just gonna give it 20 seconds, although we've already gotten about half of you. Very nice. Looks like most of you that have responded are planning to attend the network devices and systems course tomorrow. Hopefully there will be some level of continuity between our course today and tomorrow's course. But for now, I think I'm glad that most of you have attended most of the foundational courses in the past few days, and in the interest of time, I'm going to get started. Um, so hello everyone. Welcome to the nth day of the CQN Winter School for this year. My name is CJ. I'm a PhD candidate in applied physics, and I am your co-instructor for this course on integrated photonics platforms for quantum networks, alongside my advisor, or as I like to call him, my boss, Marco Lantra. We are going to start with roughly Marco and I will be trading off different sections of the presentation. There will be a couple of polls, mainly in my section of the slides, that so please keep an eye on your Zoom. And the Q&A box is open for questions and for raising hands, and whoever's not actively talking, will be trying to monitor and respond as time goes on. So without further ado, I'm going to hand things over to Marco to begin the talk with a quick introduction on electromagnetism from the very early days, as it were. Marco, please.
Yes, can you click? Excellent. All right, thanks, CJ. I'll just make a small correction. I'll say CJ is the main event here. I'm just sidekick. I'm opening act for CJ. CJ comes in the end. Basically, we'd like to share with you, first of all, welcome, and I wish I could see all of you, but I can't. And we will share with you a little bit about integrated photonics, as CJ mentioned. Much of it was inspired by classical applications, but these kind of classical applications of photonics actually have enabled a lot of progress in quantum that you will hear mainly in other presentations as well. And so, like, story of photonics, the way I structure this basically kind of more or less starts with the invention of a laser and then optical fiber, which has really enabled this idea that that information can be transmitted in optical domains. And this is, as you will see, optical communications are the main and the lowest loss communication challenge when you need to go over long distance, and are making actually really allowing us even to communicate right now, as you will see. Then once you have lasers and waveguides for light, like optical fibers, you can turn the power of the laser a little higher, And then you start seeing all kind of interesting nonlinear phenomena, and that's basically what Nico Bloomberg at Harvard has kind of pioneered, amongst many others. This idea is that you can use light and material to generate new colors of light. And CJ will actually talk a little bit about this in the context of photon pair sources and a few other things. Next slide, please, CJ. And so here, basically, we're talking about optical communications, and this map is Facebook connectivity map, and that shows basically number of data transmitted through optical fibers, which are these like faint lines going underneath the oceans, and also very bright light on the continents. So basically, is basically we are connected due to the fact that optical fibers can send vast amount of data in a very efficient manner. And the way this works, another click, is basically we need to have sources of light on one end and then receivers of light on the other end. And the simplest way to do this is basically take laser pointer and turn light on and off. This would be your source of light, basically a light emitting diode, laser pointing, blinking. You send this light to your optical fiber. On the other end, you have photodiode that receives light and converts it back to electronic domain, and that's how you can go from electronic data on one end to electronic data on the other end. In between, you have optical fiber that allows you to go over long distance. This is the simplest way to do it, but it's also not the best way to do it. And the reason is when you turn laser on and off very fast, and today communication rates go, many tens of gigahertz, hundreds of gigahertz even, which means, what is this? 100 billion times per second, you are switching light on and off. Lasers tend to go a little crazy. So the way to do this is basically keep the laser on at all time, as shown in this inset here, and then you use a device called modulator that basically, so you can think of it as very fast electro-optic shutter. And we'll come back to pretty much first, maybe half of my part is going to be building up towards making these modulators, because they're very important components for classical communication, but also very important components for quantum communication, as you will see, as well as quantum computing, actually. So basically, this electro-optic shutter allow you now to take data from electrical domain and put it in optical carrier, send the light via optical fiber. On the other end, you need to have, again, a very fast photodiode. There's no way around it. And then signal gets converted back to electronic domain. And so this communication is what motivated development of much of the photonics. But if you go to the next slide, you'll see that there's many other emerging applications, actually, that now we can tackle once we have lasers and sources and fast switches and detectors and all that stuff. And here's just some examples that we at Harvard like to think about a lot. Is quantum communication, and actually in the center, in CQN, broadly speaking, quantum computing and quantum communication is going to be kind of focus of today's presentation, but also various forms of sensing. LiDARs, basically optical radars, are very powerful way used for ranging to measure distance very precisely, much of higher resolution than radars, for example, and of interest for self-driving cars. And people go even as far as actually looking into optics as accelerators for classical computing. So basically using photons not only to transmit information, but also do computation itself. And so in the next slide, basically, we kind of motivate this idea of building now quantum networks. Like, why do we need quantum networks? Why do we need quantum interconnects? Well, basically, similarly, how actually optical communication and optical interconnects in classical domain emerged from the need to connect a bunch of computers to make even bigger computational resource and also communicate information over long distance. Similarly, as quantum resources emerge, there is a need to connect quantum computers, quantum sensors, atomic clocks, and whatnot. And for that, it can be, one way is to basically use classical networks to go from quantum to classical domain, communicate information classically, and then quantumize it at the other end. But that's not very powerful for a number of reasons. So really what is emerging as a need is having this network that is end-to-end coherent, that network that can essentially establish and distribute entangled states of light in this case, and because also light can be entangled easily, quote unquote, with other types of qubits. And so this kind of idea of that light is very low loss and very efficient and high bandwidth information carrier also is useful for quantum processes. So if you go to the next slide, then basically we motivated kind of three reasons why, at least in our lab and many labs around the world, you may want to make such a interconnected quantum system. Well, first, on a lab scale, there is a lot of interest in connecting quantum computers to make sort of quantum computing in reality. We will most likely need to rely on modular quantum computing. And in the case of superconducting quantum computing, this is motivated by the fact that superconducting qubits, that are one of the forefront platforms to realize quantum computers, they basically simply number of qubits that need to be placed inside these dilution refrigerators, where basically these qubits operate at very, very low temperature on the order of 10 of millikelvins. Number of qubits and number of wires, as you can already see, is so large that simply cooling power a single refrigerator probably is not going to be enough. And so the idea is from classical computing, again, where we went for similar thermal reasons, actually from single core to multi-core processors, actually applies here as well. We want to have these bunch of smaller quantum computers that are connected. And so basically the connectivity is quantum modulator, if you will. If CJ if clicks, then you're gonna show the way one we are building. My student Hannah is actually working on this. This is so-called quantum transducer. It's a device that allows you to connect two superconducting quantum qubit using light by taking advantage of very efficient electro-optic effect, the same effect that's used to make high-performance modulator. In addition, superconducting computers, one more click will take us to trapped atoms and trapped ion quantum computing. Similar ideas apply. Yeah, most likely modular computing scheme will be needed there. And there, what we are working on are basically this integrated photonics platform, one more click, that allows you to actually send optical signals and receive optical signals from these to and from atoms in order to provide this connectivity. So integrated photonics is going to play an important role here, we think, as well. And finally, basically, if you really dream big, then these networks that I showed you from lab scale to chip scale, maybe one day can grow to networks that are continental scale and allow you to be quantum secure internet, essentially. That is one reason, but another reason, after one more click, basically you'll see is having these really large quantum networks of quantum sensors. Quantum sensors can leverage laws of quantum mechanics to increase sensitivity or whatever, in this case, for example, radar system. But if you have many of them, then the actual aperture of such a system increases. And if they are actually connected in quantum fashion, but if they share entangled states, for example, then it has been shown that in this paper that I'm mentioning there, this can be very efficient, very powerful way of doing this. And so on the next slide, basically, we showed kind of this vision. And there we are building, again, integrated quantum systems to connect these things. And on the next slide, basically, we are showing this vision that our Center for Quantum Networks has built, and the goal is ultimately to enable these continental scale quantum networks by building various devices and chip scale systems that will enable this. And so the next slide, just briefly, just want to motivate again, what is it that we will need to build such a network? Well, first, without going into details, but I hope this is going to be discussed in other session, is we will most likely need some sort of memory because single photons do not travel very, very far inside optical fibers, and these quantum networks will almost certainly rely on single photons or potentially also squeeze light, which also is relatively fragile. So it cannot propagate very, very far. So we will need to make so-called quantum repeaters. We will likely need quantum memories to actually enable long-distance communication. One way to make quantum repeater is to leverage basically quantum memories. And the easiest way to think about it is to have trapped atom. But light and atom don't like to interact very strongly. Therefore, we need to place an atom in an optical resonator, which is going to pop up after one more click. And so this resonator allows basically light and atom to interact very, very strongly. In addition to atom, we need often we need this first atom is used to communicate information, but often we need to actually have atom that stores information while link is being established, right? So this can be a local memory on your computer where your communicating atom is trying to establish the link with another node that comes after another click. And basically, it looks pretty much the same. And these two, once network is established, basically can shuttle photons back and forth. And so for this vision to become reality, basically there's a number of things that we'll need. As you will see, there is a optical cavity. So maybe CJ, if you can click on the list of the things. And I apologize for calling CJ to click. It turns out my PowerPoint doesn't want to show these beautiful slides that CJ and I prepared. So bear with me. So basically, we will learn today a little bit how to make these optical cavities. CJ is going to talk a little bit about some memories as well as different types of sources and different types of detectors that are all needed to actually prepare these quantum states and establish entanglement and read out the states of the atoms. Okay, so CJ, I think you're next.
Yeah, and so that was the um preamble, and actually now we're gonna step into an introduction part where I will well, it will be a little bit of a recap both of what you saw in previous seminars and also a little bit of what Marco mentioned before, just in a schematic way that our talk will subsequently be organized against. So just to recap, in a quantum network, what Marco alluded to is that photons are used as flying qubits to send information over long distances. And it also needs certain optical components that Marco mentioned briefly earlier. And also we'll talk about how in photonic integrated circuits may be a path towards scalability and cost reduction for large-scale implementation of such networks. And then finally, we'll ponder a little bit what kind of materials will be suitable for photonic integrated circuits by drawing an analogy to how silicon is ubiquitous in electronic integrated circuits. So, and all of this is in service of answering or encouraging you to think about this main overarching question of this that you should be thinking about in this seminar is what do you think makes a good integrated photonics platform for the devices that you need in quantum networks. So just very quick recap, what makes a quantum network? You have nodes, you have a quantum information in the form of a qubit in this nice, represented by this little nice ket notation that you've probably encountered in the past seminars, and you have a channel that you send it across, where you send it over a large distance. If we just translate this into components, what you need is a source, some kind of encoder, a channel to send it over, and a detector. And very quickly, you run into problems in this, even in this very basic sketch of two nodes and one link, which is that there's loss. No matter how good your optical fiber is, in some sense, your quantum information will eventually get lost due to attenuation. And also, there's a problem of decoherence, where if you send a photon over, if you send quantum information over a long distance and it interacts very strongly with an environment, what starts out as a pure quantum state will interact with the environment and will interact with it and then eventually turn into a mixed state where you can think of it as it being entangled with the environment and therefore you can't back out the information that you originally had. Now, for both of these problems, it turns out that photons, despite kind of its various drawbacks, are still one of the best carriers of quantum information for long distance transmission. The first thing is that the loss is relatively low. We can actually leverage a lot of existing fiber optic telecommunications infrastructure that allows near infrared light. So if you think about wavelength, it's about 1200 to 1600 nanometers, or 1.2 to 1.6 microns. So about which is invisible to the naked eye and like basically roughly like twice the wavelength of red light. Can be transmitted with extremely low loss of about 0.3 dB per kilometers. And roughly what this means, this figure of merit means is that you lose half of your light or half of your photons every 10 kilometers, where Yeah. And then the additional thing that makes photons really good is that the interactions between a single photon um, and a transparent material is relatively weak. So you have relatively low decoherence when you send photons over a link like an optical fiber, which means that you're picking up less kind of your state is not interacting with the environment as much and decohering. Um, so even after all of this, as Marco mentioned, we still need a quantum repeater, which I think in previous iterations of the course have been covered in more detail in some of the other short courses. So we won't spend too much time on it. We'll talk about it a little bit. We can talk about it a little bit at the end if we have a little bit of time. But in general, all the components that we need um, uh, for for preparation, manipulation, transmission, and readout of a photonic qubit, as we would like to implement them for a quantum network, are implemented as photonic components. And so this is how we'll organize the talk, which is we'll talk about some sources, some devices such as switches, modulators, polarization rotators. We'll talk a little bit about waveguides, which we can split into within a node where we route light around for when we process it, or in the form of waveguides, or if we are sending it across large distances between nodes, then we'll talk about optical fibers, and then we'll talk about detectors, and then finally, quantum repeaters actually ends up being like a kind of a higher level device that kind of is made out of all these components listed above. And so where does integrated photonics come into this picture? Well, the motivation for going to integrated photonics is to kind of take inspiration from integrated electronic circuits, where by kind of moving into a kind of a by miniaturizing every individual transistor, you kind of progress from like computers that used to be room size to something that where many processors can fit on a single wafer, and therefore can be manufactured cheaply and cost efficiently, so that we can have like many computers in our pockets, in our homes. And ideally, if we can implement all of these photonic quantum information processing at quantum in various nodes of a quantum communication networks, then that would pave the way towards kind of having a large scale network that can allow you to have secure communication from end to end, from your home to, like, let's say your mom's house or something, you know. And so with that in mind, we will find that in terms of integrated photonics, however, there are actually, if you look into literature, there's actually a lot of materials that people have been studying and exploring to make these integrated photonics. And so it's unlike in electronic integrated circuits, where many decades of research it has still held up that silicon is one of the best is kind of the material to base all of your transistors on. We don't really know yet what would be the best kind of material to make photonic integrated circuits out of. And so here as a little exercise for you guys, maybe just for like a couple minutes, I'm going to put up a list of materials that you might have encountered if you've seen any literature on integrated photonics. If you haven't, that's totally okay. And kind of reflect a little bit, just guess like you think might what you think might be kind of the analog for photonic integrated circuits as the best material for photonic integrated circuits, just as silicon is for now the best material for electronic integrated circuits. So I'm going to launch a Zoom poll shortly, and then here are a random list of materials that to get you started. And let's give 2 minutes for this. Uh, okay, okay. So far, lots of people like diamond. There's one silicon nitride. All right. Okay, some people like InGas. Okay, cool. Oh, diabates. Okay, okay. Ah, there are a few that think that it's a material that kind of that it's a novel material that we don't know yet. Okay, and I'm just gonna let the timer run to 2 minutes, just so we can get responses.
CJ may have figured out how actually use another computer. I think I may be able to share my screen eventually.
All right, thank you then. I will switch the sharing over to you when you start your next section.
Yep.
Uh-huh. Uh, looks like a lot of people like diamond and lithium niobate in this seminar. Marco, you must be happy, I guess. Um, but there's a lot of silicon nitride, which is actually one of the most mature photonic integrated material platforms for photonic integrated circuits at the current moment. And I'm just going to end the poll now and share the results so you can get a sense of what kind of your peers think who are attending the same seminar. So lots of good answers. I don't have an answer for you. I don't know myself, but it's interesting to see kind of how what you guys think. I think there are a few of you that really are really strong believers in 3.5 3.5 materials. Those are really good for active devices, such as detectors and kind of laser sources. And surprisingly, silicon only had one person, one attendee, even though silicon, I think, is one of the longest developed kind of material platforms. And some of you think that it is the best material platform for photonic integrated circuits, kind of scalable photonic integrated circuits is still sometime in the future. Cool. So okay, with that in mind, I'm hoping that the rest of the talk will kind of give you a little bit of a framework to kind of think about all these, to organize your thoughts about what you know about all these different material platforms and to evaluate them in kind of the context of what are the important devices and the device figures of merit that are important for for a photonic integrated circuit that goes into a quantum network. So the content overview as follows. That was the introduction. And then Marco will very shortly take over to talk a little bit about passive and active photonic circuit elements. Most of this section will start off classical because as we will find out, a lot of the best photonic a a well-performing integrated circuit component, photonic component that is suitable for use in a quantum network is often the kind of best classical device that you can possibly make. So that's a nice thing about photonics, where you can kind of get for free good performance when you just make a good classical device. Uh, and then we'll talk a little bit about light sources and detectors, where half of it will be handled by Marco, who will be talking about kind of things that are a little bit more traditional, like just regular like detectors and laser sources. Well, I'll take over and really get into the meat of the quantum light sources and detection for single photons. Um, and over the course of the seminar, I just want you to keep thinking about it means to be a what it means like to be a good platform for photonic platform for quantum networks as you hear about all of these components that we need. So without further ado, I'm gonna send it over to Marco, who will start talking about the power of integrated photonics. And I will stop
Me?
sharing now.
Hey, okay, it's me. All right, good. Well, good to see you guys again, that I have a working computer. Uh, And yeah, I really enjoyed seeing the results of the poll, and hopefully by the end of this presentation, you'll see that all of you are right, more or less. Actually, I think everybody's correct in a way. Okay, so
Yeah.
that about photonics is what CJ says. I'd like to actually drive this home, but slightly differently. Nice thing about photonics is that you can go far in quantum photonics, quantum connectivity by using classical devices, and I am, as I like to say, classically trained engineer, whereas CJ is quantumly trained applied physicist, I suppose. But actually, even more like importantly, by developing quantum photonics, you end up making some really low loss, super high efficiency devices that then can have very positive impact on classical communication as well, which is why I'm personally actually super excited. Another nice thing for somebody that's simple-minded person like me is that actually you can go far in photonics by using a very small library of elements. So our alphabet is sort of shown here. There's several simple elements that allow you to pretty much build everything. These are passive components, and then by adding some gain, or by adding some material with electro-optic effects, or by adding materials that have memories in them, you can actually make pretty much anything. So you will need some waveguides, which are actually not shown here. I just realized, but everything here depends on a waveguide. Oh, here's a waveguide. This is Y splitter, which is our beam splitter. There's different types of splitter. There is yet another type of splitter. Splitters are very important. All of these things are different types of splitters that have some pros and cons. This is network of splitters that allows you to split light from 1 to 4 outputs, as you'll see, super important. Resonators, filters of various kinds, gratings that can also be used as a filters. Pretty much all of these things are filters, couplers, and so on and so forth. So we'll touch upon many of these, not all of them, but because we touch upon many of them, we are not going to go into great detail of any of them, but it's give you, I think, a nice overview of what's important here. Okay, so waveguides are fundamental building blocks. As I mentioned, beam splitters are kind of next in line, and with them you can do many, many things. And I will assume that most of you have seen E&M and Maxwell's equations and whatnot, and I'm not going to go spend a lot of time here, especially its most fun content is actually in the second half, and CJ talks about it. So I just want to point out that in free space, where electromagnetic wave propagates, we often think of it as a plane wave. As a plane wave, we'll have polarization field is going to be important for our waveguide. It has frequency, and it has wave vector. And so definition of each of these shown here. Frequency, this is angular frequency, is 2 pi frequency of light, which is in the telecommunication wavelength trained around 200 terahertz. And wave vector basically tells you about periodicity in space, similar to how frequency tells you about periodicity of this wave in time. And we will, at the beginning at least, I will be showing some of these dispersion diagrams. They're a pretty useful thing to understand because a lot of stuff in photonics, unfortunately, you cannot actually write closed form solutions. You typically need to resort to numerical modeling. So kind of understanding how having intuition, understanding these dispersion diagrams is very helpful. So what we are showing here is how the frequency of this wave is the function of wave vector, which is basically frequency in time as a function of frequency in space, if you will. And the two are related in free space by the speed of light. And in air, this is speed of light in air. If this is big block of silicon, this will be speed of light of silicon, which is related to speed of light in air as speed of light in air divided by refractive index of silicon, right? So now once you and this all fine and dandy once when wave propagates in free space. Once actually you start introducing interfaces, even if you just have two half spaces, at the interface light can actually bend, and then we need to introduce boundary conditions for electromagnetic waves and a few other things. But basically for us, mainly it's going to be important that if light is trying to leave medium with high refractive index, let's say water, and it's trying to get into air, like shown here, there is a range of angles that light is incident in, and above this critical angle, that if light incident angle of light is larger than this critical angle, light is totally reflected. This is called total internal reflection. At this point, all of your optical energy is trapped in this case, let's say the water. And this process, this is rave picture formalism. In reality, when you think about it, so in terms of Maxwell's equation, you find out there is actually phase associated with this reflection, and this phase will pop up here and there because I copied pasted slides for our grad course. So I just want to mention this as a disclaimer. So, and you can see it here that the light is not instantly reflected. It kind of almost penetrates a little bit into, there's going to be a evanescent field on the other side, and then it comes back. Okay. So this is one interface, but the way you make optical waveguide is you put two interfaces together. So maybe I'm just going to skip this slide in the interest of time. And so what you can do, you have one interface between, let's say, silicon and silicon dioxide. Okay, it's popular material choice in integrated photonics. Then light is going to bounce here and going to come down and bounce there again. And if thickness of the silicon layer is properly chosen, at this particular frequency, at this particular angle of incidence, you will be able to trap light and form, we call it optical mode. If you change the frequency, you will need to change angle of incidence a little bit as well, and this all can be calculated from an equation similar to this one. We call this mode, but it has only like half of oscillation in space here. We call it fundamental mode. If waveguide is thicker, then for the same angle of incidence in this interface, you can actually, light can swing a few times, twice in this case, make almost one whole period, and this is what we call it like high order modes, like this, and these are high order modes for this particular frequency, this particular angle of incidence, but here we needed to make waveguide thicker. In reality, actually, the way this works is we have our waveguide, as shown here. This is so-called slab waveguide. We have core. This is the dark blue region. It has high refractive index of N1, let's say silicon, index of 3.5. We have cladding, which is refractive index that's lower, let's say 1.5 in the case of silicon dioxide. And then by choosing which frequency of light we propagate through it, we need to figure out what is the incident angle of light that's going to be incident in this interface that's going to allow light propagation. Okay, so this is going to define the mode. So basically, our dispersion diagram that used to be these straight lines before, now the straight lines actually become these curved lines, and these are different modes. So these slab waveguides. And again, on y-axis I have frequency, on x-axis I have propagation constant. But now this is not a wave vector anymore. It is a wave vector projection on the direction of propagation. We call it beta. So it's going to be basically, it's going to tell us what is in this picture here. You see the light beam still goes up and down at a particular angle. Beta is going to be a projection along Z, which is this projection here, parallel to the interface between core and cladding. A projection of k vector to this axis is what we call wave propagation vector, propagation constant beta, right? So basically, this is my fundamental mode. This is my first or higher order mode, second higher order mode, and so on and so forth. Okay, so this, and then we are not going to go into math a whole lot here, but for slab waveguide, you can actually find this dispersion relationship exactly, which is actually quite nice. And this is probably one of few things you can do exactly without using numerics in this business. And these are, I'm showing here now, first order mode, fundamental, and these high order modes, dispersion diagram of which is shown here, right? For the same wavelength thickness in this case. Okay, so now what is a good waveguide? Is it better to have thicker waveguide or thinner waveguide? Is it better to have one mode or more modes? Is it better to have low index contrast or high index contrast? Should these waveguides allow one flavor of light, one polarization of light? We can gloss over this a little bit to propagate or not. Do we want to have more or less dispersion? Meaning, do we want to have more or less curvature here in these modes? Is this better or worse? All of these things, I wish I had poll set up. It would be very interesting to hear what you guys think. But basically, really is the function of what you're trying to accomplish, right? And so if you want to send a lot of optical power through waveguide, you probably want to need thicker waveguide. On the other hand, if you have thicker waveguide, you will have many optical modes propagating in it. And these optical modes, I'm just going to mention this briefly, will propagate with different group velocity, right? And actually even with different phase velocity. So for example, for particular frequency, what I mean by this, let's say I choose this frequency of light here. Let's see if my pen here works. If I choose my frequency of light to be here, all right, then I'm going to excite this mode and this mode. So in my waveguide, I want to have two propagating modes. And they will have different phase velocity. Phase velocity is going to be basically determined by the slope from this point to origin and this point to origin. Okay, but also they have different group velocity, and group velocity is determined by derivative of this curve, d omega over dk. Group velocity tells you how fast energy propagates. So you can see immediately that because of different slopes, either for phase or group velocity, this mode and this mode will propagate different speeds. And so that is a problem now if you have thick waveguide, and we said, let's say I want to have thick waveguide to have a lot of optical power in it. Why I want a thick waveguide? Well, otherwise power density is too great. Maybe I start seeing nonlinear effects, even I don't want to see them. But now if I have thick waveguide, I have higher order modes, they propagate at different speeds, my pulses, my ones and zeros start spreading, and that's not good. So you really need to think about is, there's no clear answer. On the other hand, also thick waveguide we use in our lab a lot. Maybe CJ touches upon this later, because thick waveguide minimizes overlap of optical field, or rather wide waveguide, not so thick waveguide. Well, thick as well, but mainly wide, minimizes overlap of your optical modes with surfaces, which minimizes the losses. And I'll come back to that point a little later. So, this is very important to keep in mind and think about. Often waveguide, having said all of this, often good first step is to consider so-called single mode waveguides, which are basically waveguide thickness is chosen such that it allows only one mode to propagate a particular frequency of interest. And thickness of such a waveguide is actually a function of wavelength as well as index contrast. But good rule of thumb is it's roughly wavelength divided by 2, give or take, right? So if I want to have waveguide for 1 micron light, waveguide is roughly going to be half a micron thick, unless we're talking about optical fiber or so-called low index contrast waveguide, where these cores can be much, much larger. So because now, if let's say you have, diamond in air or silicon in oxide or lithium niobate in air, waveguide index contrast is large, and this argument of a single mode being wavelength divided by 2, that means these waveguides are roughly half a micron thick, and most of the time light comes from big optical fiber, it becomes actually a challenge bringing light into the optical waveguide. And so we in the lab spend a lot of time and money and a lot of human bandwidth are actually figuring out ways to minimize these, we call it insertion loss, increase the efficiency with which we can bring light either from the free space via lens, as shown here, or from optical fiber using various techniques on chip. And like easy, just FYI, easy like in industry is 3 dB, roughly 50% of light gets lost. In our lab, 3 dB is good day. If you don't do anything, maybe we lose 60, 70% of the light. But some, like in quantum communications, people have recently demonstrated 99%, for example, insertion efficiency, which is amazing. We also had some collaboration with AWS that pushed this, and actually CJ was involved in some of these 99% as well. So this is very important, not so easy to do. Okay, there's many strategies to do this. I'm listing here some. There are like various directional couplers, evanescent couplers, graded couplers, prism couplers, tapered fibers, photonic wire bonds, spot size converters, or maybe terminology that we have heard. We are not going to have time, unfortunately, to go into this. But basically, two guiding principles are either you expand the mode of your waveguide a lot by making waveguide narrower and narrower, and therefore light pushes out, or you do some sort of evanescent coupling where you are bringing another waveguide nearby and try to kind of adiabatically kind of tunnel into your waveguide. As I mentioned, in practice, rarely we work with slab waveguides. We all typically work with waveguides that have confinement in 2 dimensions, and the 3rd dimension they propagate, where slab waveguide has confinement in 1 dimension only. And therefore, actually, these turns out to be very difficult to design. You cannot just you cannot find closed form solutions, so you need to use numerics often. And so we will not be teaching you that. Important consideration for waveguides are losses. Losses come in several shapes and forms. First, material. If you pick material that's not transparent, that's on you. And that means that you will have tons of loss. If you pick silicon, you want to work invisible, that's never going to work really well. But if you pick silicon, you want to work in telecom wavelength, that should be good because bandgap of silicon is actually wider than the energy of telecom photon. So light is not going to be absorbed. But if you dope silicon, you will have so-called free carrier absorption. That's I think about it as a plasma effect. It's like silicon becomes more metallic and these free carrier absorb light. That's not good. Eventually, bond carriers can also give rise to absorption as well. So, that is one issue, and bandgap we talked about. Also, you have scattering. So this is not material related. It is basically the fact that when you make these waveguides, they're never perfect. So there's going to be bumps on the surfaces of these waveguides, and light will scatter on these bumps. Basically, total internal refraction condition is going to be spoiled, so that's not very good. If you bend waveguide, you again spoil total internal reflection condition, and light can leak out. So there's bending radius that you need to satisfy in order not to lose light, as shown here. And then also at high powers, you can have no linear effect. Maybe two photons will be absorbed instead of one photon. Maybe you'll have some Raman scattering, maybe some brilliant scattering. Maybe you start seeing some four-way mixing, curve lensing, all kinds of crazy stuff that can result. Actually, very interesting stuff, not necessarily crazy, very useful stuff. But if you don't want to do it, then it's not very useful at all. Okay, so maybe I will skip this in interest of time. I will just point out that this is very important to kind of keep in mind. The way we think about light propagating in lossy medium is that essentially, in addition to this kind of phasor that we see in the form of plane wave propagation, there's going to be, because this k vector is actually 2 pi divided by lambda times refractive index. In lossy medium, refractive index actually becomes complex number. It has real part and imaginary part. Imaginary part gives you loss. And loss we define as basically 4 pi divided by alpha lambda times imaginary part of refractive index. It's actually not definition. It really comes from this equation. And why is it 4 and not 2 pi? It's slow, subtle. It is a consequence of the fact that this absorption factor we define for propagating power, not for propagating field. And because power is field square, you have an exponent, another 2 that kind of eats up this half. So this is a loss for waveguide that has some loss mechanism that can be phenomenologically or physically represented as imaginary part of the refractive index. It's good to keep in mind. You'll see this later. I'm going to skip this as well. And skip dispersion. The CJ is going to come back to that later as well. Okay, so important components of these integrated photonics, as I mentioned, are beam splitters. And so beam splitters, maybe some of you played in a lab if you're working in optics lab. So they're basically these beam splitter cubes. They can be polarization like sensitive or not, right? And the way they work is actually very, very actually cute. They rely on this total internal reflection that I talked about before. If I just have, you can think about these prisms as a cube that consists of two triangular prisms, okay? And so if I just had one triangular prism, if I come in with an incident beam of light, and if I choose this prism angle properly, light will basically be totally internally reflected at this interface, and all the light is going to go up. But remember, there's this evanescent tail that I mentioned because there's a phase shift. So what happens now, if I bring another prism, but don't quite put it in contact with the first prism, but leave small gap, I can have attenuated total internal reflection. Basically, some of this evanescent field is going to tunnel into this other prism and leave through this way, right? And some of it is still going to be reflected. So it's attenuated total internal reflection. It's not FTIR, but or rather frustrated. Okay, that's where F in this case comes. Frustrated total internal reflection. And so basically, you can, by controlling how far these prisms are, you can make actually 50-50 or 90-10 or whatever other splitting ratio beam splitter you want. Well, it turns out you can do the same in integrated photonics. So let's consider two slab waveguides. So far, we only had one. And let's say this slab waveguide is designed to support only one mode. In this case, it's fundamental mode of the waveguide. Once I bring, and this fundamental mode of the waveguide, we say it's eigenmode of this system, right? This comes from some group theory and the symmetry, basically, group of this waveguide, which is in this case has only one reflection symmetry point in the middle of the waveguide. Once I bring another waveguide, this is not eigenmode. Now, eigenmodes of this system are even and odd superposition of the single mode. This is similar to two coupled quantum wells. But okay, but I'm not excited. And nice thing about eigenmodes is once you excite them, they propagate forever without being disturbed. So if I excite this eigenmode or this eigenmode here, they're going to propagate happily. But if I send this light in, it's going to be decomposed into some combination of even and odd eigenmode, input light. But this input, these two eigenmodes, new ones, even and odd, have different phase velocity. We've seen that already, right? We've seen it in dispersion diagram. They will have different slope. They have different phase velocity, which means they will propagate with different speed. Okay, so they will have different phase velocity, propagation constant. And so after some time, they will be out of phase. And once they're out of phase, this plus here sign becomes minus sign. They get subtracted up to constant factor in before. When they get subtracted, you see this power is going to subtract from this power, this plus minus minus this field is going to give you positive. So basically you can see that all of the light is now going to be in the second waveguide. So using the simple argument and kind of you can see how y-directional coupler, this is called directional coupler, by the way, when you take two waveguides together and they're close enough, they need to couple. If they're too far apart, they cannot couple. Is this a question for me? No. They need to couple and then they propagate different speed. And eventually after one kind of coherence length, if you will, they'll be out of phase and light is going to be, we say, completely dropped to another port, right? So if I'm looking at the light in this top port, there's going to be a lot of light after a certain length, no light in this port, and then light is going to come back when these guys become in phase again. We can get a factor of 2 pi. And so that's exactly what we do on chip. We make these directional couplers, and they basically, look like two waveguides that are nearby, okay? And light is kind of going to jump back and forth and eventually be split in whatever ratio we designed this to be by controlling spacing and controlling the length of this device. I'm not going to spend any time on this. I just want to say that this actually phenomenological treatment is very powerful and it can be further extended to get not only qualitative but quantitative estimate of how this works using so-called coupled mode theory, which I encourage you to consider if you haven't seen. It's extremely powerful tool in integrated photonics, mainly because there's not much you can do. There are not very many problems you can do with closed form, so you often need to make some approximation. And coupled mode theory allows you to make some of these approximations. Long story short, basically you will, due to the coupling of the two waveguides, you'll see that if I put power in the input, electric field A1 here or an electric field A2 here, that basically how much electric field I have anywhere in this coupler is going to be the functioning of various constants, and that are a function of how close these waveguides are and how long the coupling section is, as I mentioned. And so for particular length and particular separation, we can make so-called 50-50 splitter. Okay, and this is a very useful one, as I'm going to show you. And you'll have to believe me in some of these constants I'm going to throw at you, but they follow this coupled mode theory formalism. Basically, if I make 50-50 beam splitter, then it's represented by matrix, looks like this. So these are just numbers, these beta 1, kappa 1s, kappas, and whatnot. For 50-50 beam splitter, in a case of symmetric waveguides, meaning both of the waveguides have exactly the same profile, basically is this matrix. It can be exactly derived with maybe another page of math. And this tells us what is the electric field amplitude in top waveguide and bottom waveguide after the splitter, okay? And you see that power is going to be split. 50-50 means 50% of power is here, 50% of power is there, which means the amplitude is related to square root of 2/2. in books, I just want to point your draw your attention to the fact sometimes in books there's no these minuses here, and this is due to the fact that when we picked in this particular set of lecture notes, I chose to use this phasor diagram that has minus sign here. Often there's plus sign here, and this plus sign would result in these minus signs becoming plus. This is not so important. Just like if you copy paste notes from different books, then there may be some inconsistencies. That is, as long as you stick with this one formalism, everything is good. So that's our 50-50 beam splitter. Okay, so now what I want to make modulator, Mach Zehnder interferometer / modulator / switch. Okay, I told you at the beginning, modulator is a very important component of optical communication, so I want to build this modulator. So this is static beam splitter. It's always going to split light 50-50. But here's what I can do. I can add another section now of waveguide with some electrodes around it. And this section of two waveguides that I'm going to describe again with this kind of matrix formalism. That's a consequence of a couple of materials I mentioned. This following matrix. Basically, when light propagates here, it's going to acquire some phase. So here's the phase. When light propagates here, it's going to acquire some other phase. Why does light at the top requires additional phase? Because I left the opportunity for these electrodes to do something interesting here. Okay, and then if I follow up and with another 50-50 beam splitter, okay, another directional coupler which has the same matrix as the first one, then I have described this system completely, and I can find output as a function of my input vector, right? I can find electric field at the output as a function of the electric field in the input. I just multiply these matrices, so-called transfer matrix approach, and I end up with something like this with a little bit of little bit of math, okay? So basically and this phi is the phase that is introduced by this one additional electrode on top. So you see that output, light in the output arm, 1 or 2, is related to how much light I put in the input, but now is the function of this phase, which I actually can control, okay? And so this is super powerful because this allows me to do basically a few things. First, maybe let's go to this equation real quick here. If this phase is pi, okay, and I'm feeding light, A2 is 0, for example, okay, you see that light is going to be only in one of these basically waveguides, okay? If a phase is 2 pi, then basically light is going to be the other waveguide. Okay, so excuse me. So this now can be used to make various types of modulators, or various types of controlled or active photonics element that are not only passive, simply by applying something here that's going to change the phase of light. And I can change the phase of light simply by changing the refractive index of the waveguide that light propagates to, which can be done simply by heating, for example, this arm of the waveguide using heaters, leveraging thermal optic effect, as when you're heating some refractive index changes. That's, by the way, why you have mirage in desert or on asphalt, hot asphalt, because air close to the surface gets hotter and it has different refractive index. I can inject some carriers that's going to give me a loss, but also is going to change refractive index. I can actually move things around using MEMS, micro-electromechanical system. That's going to also give me some phase change. Or I can use electro-optic materials, which are materials with so-called Pockels effect that basically allow refractive index of material to be changed by applying electric fields. And so this turns out to be the most optimal in terms of speed and energy consumption, actually, the electro-optic effect. So silicon photonics, some of you mentioned earlier, silicon is good material, and it's absolutely true. It's one of the important materials in classical photonics. Unfortunately, silicon, to make this modulator, you don't have electro-optic effect. If you make MEMS device, they are limited to speeds of maybe megahertz, tens of megahertz. Depending on application, this could be plenty good or not fast enough. I said sometimes you want to go to hundreds of gigahertz. So what people have done, they inject carriers or they sweep carriers out. So they're using carrier dispersion to change refractive index. But unfortunately, and this has been a really powerful way of doing this, but unfortunately it results in huge loss. And so without going into detail, I just want you to know that this carrier dispersion comes at the expense of very large loss. Okay, in contrast, there's materials like, and let's not worry about this chart for now. There's materials that do have electro-optic effect, like lithium niobate. Some of you mentioned that as a promising material for quantum photonics. And indeed, it is very promising because you can change refractive index simply by applying this. Actually, it's not Chi2. This is electro-optic coefficient. My apologies. You can change refractive index by applying electric fields, okay, without any loss penalty. And that's been known for a long time. And lithium niobate devices have indeed been used to make electro-optic modulators like the one shown here. But basically, you have input fiber, output fiber. You bring some electrical signals through this port, and by sending bits, bits ones and zero, light flickers on the other end. The problem with this approach is that it's very hard to integrate anything in it. And I state like the name of the game in integrated photonics, and especially integrated quantum photonics, you want to minimize number of times how did you go on and off chip. Every time, unless you are one of these amazing quantum photonics companies, every time you go on and off chip, you lose 1 or 2 dB of light for sure, often 3. So as I did say that many of them these days you can achieve loss efficiencies that are already order 99%, but it's still not common, right? So therefore, you kind of want to stay on chip as much as you can. So bring light in, do whatever processing you need to do, and then get out. But unfortunately, lithium niobate, it was very hard actually to do a lot of integrated photonics processing because it's very hard material to fabricate in. But unfortunately, and this has changed recently, and in particular was actually enabled by this emergence of thin film lithium niobate on insulator materials that some of you may have heard of. So for almost every integrated photonics platform, I actually didn't drive this message home yet. I will maybe use this slide to do so. Every scalable integrated photonics platform relies on fact that you can make that you have at least 2 materials or 1 material in air, but let's say 2 materials. One material is going to be your core. It's going to guide the light. It needs to have a higher refractive index than material directly underneath it that's going to be forming the cladding. And that material directly underneath it or directly above it could be air eventually. But when you're making these wafers, it's better be something that either has low index or that can be removed. And so this is very easy to do in silicon in photonics. It's silicon on insulator is commonplace. It is relatively easy to do in 3-5 semiconductors. It's very hard to do with diamond. In lithium niobate, it was hard, but it's not anymore. And so the way that what people do is so-called smart cut process, as shown here. So you grow these lithium niobate preforms that they look like this. Then you slice them like salami, literally using like blade. And then you take one of these slices and you implant helium, for example, inside. And to damage lithium niobate below some number of, let's say, micron, half micron underneath the surface. You take a silicon wafer, you oxidize it to form oxide, and then you take this lithium niobate wafer, put some oxide on it as well, and you put it on top of this oxide on silicon and fuse it by applying temperature and annealing. Essentially, oxide fuses. And then due to thermal stress, also lithium niobate substrate can kind of pop off, like shown here, and then you polish what leaves behind, and you end up having this very thin film of lithium niobate of one oxide and silicon. And so these wafers now are ready to be processed. And so maybe I'll skip this. So over the years, community has done a lot of work on optimizing these fabrication processes that allows us now to make these waveguides in lithium niobate as shown here. They're very, very smooth, have very low loss, 3 dB per meter. It's compared to optical fiber is giant loss, but compared to like all other integrated photonics platform, it's actually pretty good. Maybe factor of 10 away from the most promising one, which is ultra thin silicon nitride, but that one is passive, doesn't have any active components. And then using this, you can make amazing switches and amazing modulators. I'm not going to go into details of this slide. I will just say that now, basically making these Mach-Zehnder interferometers. Notice I don't have direction coupler. I have Y splitter here. This is a little easier to do, but it has some drawbacks. And now I also put electrodes not only around one waveguide, but around 2 waveguides. That is actually beneficial because This is so-called push-pull configuration of Mach-Zehnder interferometer. One arm goes up in phase, the other one goes down in phase. So phase shift I need to make is only half of what I actually need. So that requires less voltage applied to make this phase shift. And so using these modulators, actually, people are using them uh, to send vast amount of data very, very fast. So this is quite enabling technology. In quantum photonics, we are using these types of modulators as well, and this is part of CJ's PhD to do all kinds of stuff, including the linear conversion that CJ is going to tell you about. We're using both Mach-Zehnder interferometer modulators as well as phase modulators. Phase modulators in particular we use to to fix the color of photon. Basically, it turns out using Doppler effect effectively, if you send photon down the phase modulator and constantly change the phase of the light that it propagates, you can actually shift its frequency. So it's actually quite powerful approach to control the frequency of light. Phase modulators and amplitude modulators have been used. Here's phase modulators, here's amplitude Mach-Zehners to do all kind of neat stuff. This is from Dirk Engel's group. They have pioneered a lot of concept in classical computing, these machine learning type approaches in photonics. Basically, there's also a few companies that are commercializing them as accelerators for computation. Now you can use this to encode qubit, so-called dual rail encoding. If light is in top waveguide versus light is at the bottom waveguide, that encodes qubit 0 or 1. And so then this simple Mach-Zehnder interferometer with the phase modulator in one arm actually is allowed to do single qubit rotations, basically. It allows you to put one qubit anywhere on a block sphere, meaning you can control basically this qubit precisely how you wish. So this is very, very useful, a very powerful technique that's being used in, for example, Quantum's integrated photonic quantum computing networks that relies on a bunch of, you can see here, Mach-Zehners, bunch of kind of split-layer networks. There's also a bunch of Mach-Zehners. Here's more Mach-Zehners. It's all Mach-Zehners interferometers, basically, with a little bit of nonlinear optics to generate photons and whatnot. Okay, so this is, as you see, these photonic quantum computing schemes are super dependent on high performance Mach-Zehnder interferometers, and they need to be balanced. Very large extinction ratio means if I say that light is in top arm, I mean that amount of light that's left behind needs to be 30 dB below. 30 dB is 0.1%. In integrated quantum photonics, typically they want this to be 0.01 or 0.001% even. So really, really puts these devices quite to their limit, actually. And that's why people also started looking in different ways to make these splitters. This is an example of like inverse design beam splitter. And they have some advantages and some disadvantages, but we are not going to go into details of them. They can be more robust, for example, to fabrication imperfections. Okay, so next thing I want to talk, and I'm like about an hour behind the schedule, maybe not 15 minutes, maybe not quite an hour, half an hour. So I'm going to go a little bit maybe quickly over this part so that CJ has enough time to tell you exciting stuff in quantum space. I want to touch a little bit talk about cavities, and mainly because they are very important components of quantum photonics systems. Okay, so how do you form cavity? The easiest way to form optical cavity is to take direction coupler that we have described with transfer matrix similar to this one. In the beam direction coupler I was showing you so far, which was 50-50 direction coupler. This was 1, this was minus J. All right, but this now I'm showing this as arbitrary split ratio. So actually, tau is amount of light that goes through, and gamma is amount of light that crosses over. Okay, and so how do I make resonator? Well, simply take another waveguide and just loop it back. And you can see this even for yourself. Just one slide of math allows you to see that this is going to be a resonator, and so-called ringed resonator, simply by actually making a relationship between light that, like basically I put light here at port A1, light jumps here, it becomes B2, and then loops back and becomes A2. And then A2 comes a directional coupler and may stay in the ring or it may jump out and become B1. And so all you need is a relation between A2 and B2, which is shown here. It's really the relationship is there's going to be some phase. Light A2 is going to experience some phase delay with respect to B2. And there's going to be loss. This is minus alpha over 2. We talked about the losses. When you put this together with this transfer matrix formalism and do a little bit of math, you end up with the fact that light at the output of this system, waveguide coupled to ring resonator, divided by light at the input square. So this is power at the output divided by power at the input, looks like this. Okay. And so where tau is, as I said, tells you a little bit about design of this coupler, how much light goes through in a one single pass, and gamma, how much light crosses here in a single pass. If you solve this, if you were to plot it, you will find that transmitted signal as a function of phase delta, which is the phase the light acquires, looks a little bit like this. So you have series of dips. We call these dips resonances, and they happen every time delta changes by a factor of 2 pi. Okay, and these are going to become resonance conditions of this ring resonator whenever basically this delta is 2 pi. Basically, in other words, whenever I can fit integer number of wavelengths inside the ring resonator, I have resonance. Okay. I am here neglecting, actually, this is a pretty big kind of assumption. I'm assuming this direction coupler to be very short, so that doesn't contribute to the length of the ring. For this simple the discussion is good enough, but it can be also taken into account explicitly, so it's not an issue. Okay, so on resonance, transmission is shown here. I'm going to maybe skip a bunch of these in the interest of time. I just want to define a few figures of merit, and then you can go through these actually in the comfort of your own home room. Basically, I will just say that a few interesting scenarios are, where is my, yeah, so here. So I'm showing tau and gamma here, what I mean by that. Interesting condition is so-called critical coupling condition. It turns out critical coupling condition is condition where amount of light that continues equals to amount of light that gets lost in a ring, pretty much. Okay, at that point, on resonance, you see no light here. Okay, so in other words, like this transmission has perfect dip. In other ways, all the light I'm putting in the input ends up going inside the ring and it's lost inside the ring. And this is very common and very important condition. We're going to often operate in this resonance coupling condition because this allows you to put maximum amount of light inside a resonator. Why would you want to do it? If you're making modulator, this is very powerful. If I want light to interact with an atom, then I want to put all of my single photons I want to put inside this ring resonator, for example, so they have maximum chance of interacting with an atom there, for example. Okay. There's a few other interesting conditions that I'm going to skip, like gloss over, like how to make phase only modulators, very important. And another thing, by the way, in quantum photonics, the main reason why we use these ring resonators or any cavities for that matter is to get light in so that single photon can circulate many times inside the resonator, so that if there's an atom nearby, it has many chances to interact with an atom, because probability of photon interacting with atom in free space is very low because atoms are very small, photons are roughly microns big. But if photon goes around this many times, let's say thousands times, this is determined by finesse of the resonator, then this probability goes up. That's one application. In classical optics and photonics, another application is you want to actually increase intracavity power. If, let's say, you want to make laser, want to do some nonlinear optics and whatnot, you kind of want to build up optical power. You have 1 milliwatt laser, but you need 1 watt of power to do something interesting. So you send this 1 milliwatt into resonator. So it's important to consider how much light is built up inside the resonator. So for that, you can go back to your coupling matrix formalism. Basically, you see what is B2 as a function of A1. You do a little bit of math. You find this equation, not actually very hard. I mean, it's completely non-transparent when you see this equation, but if you do the math, I guarantee you in maybe half an hour you'll get there. It's very straightforward, but it is a little involved. Okay, so I'm going to skip a few things. It turns out in a critical coupling, amount of, let's take a look at this equation. So I'm glossing over several important things here. On critical coupling, amount of light that I have inside a ring resonator is proportional to 1 over alpha times L. Alpha is loss, L is length of the cavity. So this is essentially a round trip loss of the cavity. So if round trip loss of the cavity is small, this power inside the cavity can be giant. Okay. So if alpha is 0, power inside the cavity blows up, has singularity. Okay. Typically, you've seen, for example, my alpha for lithium niobate was 3 dB per meter. So if I make cavity 100 microns, I mean, this is a really small number. So I'm just going to blow up the power inside this resonator is going to be very, very large. Okay. So this is very, very useful if you want to do linear photonics, if you want to build lasers and so on and so forth. Okay. I'm just going to mention a few other figures of merit that are important for resonator. A quality factor is one of them. By definition is ratio of stored energy inside the resonator divided by the energy lost in the resonator in one cycle. Okay. And basically, practically, this determines how long does photon live inside a resonator. From this equation, you can go to this equation using Fourier transform, basically, and that is probably half page of math. And so basically, high Q factor means photon lifetime is very long, meaning and high Q factor is proportional to low loss. So low loss resonator, Q factor is very large, photon can live inside the resonator a long time, and therefore photon can interact with an atom very effectively. All right, so I'm gonna skip all of this stuff in order to, okay, so there's some interesting, we'll share this slide with you. You can watch modeling of light propagating inside a resonator and this and that. You can also, here's some pictures of fabricated ring resonators in silicon photonics, for example. They're used as filters. They're particularly useful as modulators. So here's one of the earliest ring resonators from Michael Lipson group at that time at Cornell, North Columbia, from 2005. How you make modulator out of the ring resonator? Basically, you have this resonance. This is this experimentally measured data. Okay, if you don't apply very large voltage, what happens? And this is made in silicon. You have resonance at this particular wavelength. Okay. Now, when I apply voltage, I inject carriers. I'm changing refractive index. I'm changing the resonance condition, and therefore the resonance shifts. Okay, so resonance shift, let's say to blue line. Now, if I'm sending the laser parked at this dashed line here, probe wavelength, okay, if I'm on resonance without voltage, I see no light at the output. If I apply voltage, gold line goes to blue line, I jump up, I see light at the output. So by shifting this resonance, you see light, don't see light, don't see light. So these guys can be extremely compact and dense compared to Mach-Zehnder modulators, but have several important drawbacks. But this has been actually a very versatile platform. It's used a lot today to make optical interconnects in data centers, for example. So this is nicely summarized in all these papers from Karen Bergman, for example. I'm not going to go into details of that, but it's really powerful technique, though, as I said, does have some limitations. In addition to ring resonators, you can talk about Fabry-Perot resonators, which I'm not going to talk about. And in fact, I'm also not going to talk about this either, okay? I think I'm skipping a few things. Maybe we can come back to that if there is time towards the end. How do you make, maybe I'll actually just talk about this a little bit. How do you make these Fabry-Perot resonators? Okay, maybe actually let's go back because I think CJ may need this actually. So in addition to ring resonator, another popular resonator is Fabry-Perot cavity, where basically what you have waveguide with two amazing mirrors, right? Okay. And so then light can be bouncing back and forth. And so name of the game here is how to make these mirrors. Okay. And typically the way you make these mirrors is you take materials with different refractive index and you stack them. And you control the refractive index and you control the thickness of these materials so that light bounces and each interface, it's not totally internally reflected like in ring resonators, but just partial reflection. But whatever light makes through gets even more reflected, even more reflected, even more reflected. And all of these reflected signal, if they add up coherently, you have essentially perfect reflection. And so here is an example of, for example, we call this distributed Bragg reflector. reflectivity of distributed Bragg reflector can be written as such. N1 and N2 are refractive indices of two materials used. And for example, and N is number of layers of this reflector. And you see for common combination of refractive of titanium oxide and silicon dioxide Bragg reflector, you can get 99.9999% reflectivity, which is, by the way, important for quantum, this kind of level. But only 15 of these layers. It's actually quite remarkable. On chip, we cannot put this layering down. So in chip, what we do, we make waveguide and we drill holes. So now layers are, in this case, silicon or 3,5 semiconductor, actually it's silicon, silicon, air, silicon, air, silicon, air. But in order to make this reflectivity very, very large, you need to sometimes taper these holes, okay? To minimize scattering, you need to make fabrication be perfect also to minimize scattering, so on and so forth. And CJ is going to actually tell you about this as well. So CJ, now it's moment of truth. Shall we just skip lasers? Do you need much of the lasers for your discussion of four sources or not?
Not really, but I think it would be nice. I think it would be helpful to have a contrast. Lasers are still important at the end of the day, because
Lasers
most of
are
these
very
sources need light laser anyway.
That is
Um,
true. So let me see if I can do this in 5 minutes. CJ gave me 90 minutes. I said, no, 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 I can do it 75. But here we are on 90-minute mark. So that's why I like CJ a lot. Anyways, so here are some examples of kind of these Fabry-Perot cavities made with distributed Bragg reflectors. This is the stack that I was telling you about, titanium oxide, silica, titanium oxide, except is made in 3,5 semiconductors. This forms vertical cavity surface emitting lasers, or VCSEL, that if you look at your smartphone, if you have face detection, basically there's gazillions of these lasers sitting in your phone, illuminating your face and measuring basically kind of distance, measuring the profile of your face and giving you 3D rendering of your face and doing face recognition. So basically, they are based on the fact that you can make very nice mirror and put a little bit of gain medium that we are about to talk about next and make very nice laser. CJ is going to tell you a little bit about how you can, instead of gain medium like quantum wells, put single quantum dots and single color center in diamond that's shown here, and make a very nice single photon source out of it. Here is this distributed Bragg reflector context uh, in the context of diamond cavity, where instead of, as I said, two different material, we have diamond there, diamond there, diamond there, and we can make very nice cavities like that as well. And I think that's pretty much everything on this slide I wanted to say. Okay, I will skip to the photonic crystal. Like you can make this periodicity not only in one dimension, but in 2 dimension or 3 dimension. And then we talk about 2 and 3D photonic crystals. But I'm going to skip that because actually not, it's like just kind of extension of the concept, very important. But you won't be missing much if you don't cover it. Light sources. Basically, to make light source, good light source, you need a medium that's going to generate light when you excite it. And ideally, you would like to have light source that it's excitable by electricity. Okay, so that because if you can excite it also with light, but then you need electricity to excite this other source. So eventually you need to have light source that can be excited with electricity. And so once you have these light sources, on material, you can put it in an optical resonator, and that's going to give you a laser or single photon source. Okay. And so the process of light emission is a relatively simple one. If you have medium, let's say light medium that can emit light, you excite this medium. In this case, I'm showing excitation with another photon. You take electron from conduction from valence band, put it in conduction band, or some higher order band. Okay, doesn't have to be actually valence and conduction band. And this electron loses some energy via scattering, and then eventually comes to the bottom of this band here, and then basically recombines with the hole that was left behind, and then it generates another photon. So this is a process of stimulated emission. If I put an optical resonator around this process of stimulated emission this photon can be trapped, come back and interact again with the medium and stimulate emission of another photon. And if this process continues, you can get coherent emission of light, which is basically a laser. In the process of light generation, you have, in addition to the spontaneous emission and absorption, you need to generate inversion, to generate electron with higher energy that can then be recombined and generate light. But you have process of stimulated emission, where photon already in the cavity can stimulate emission of another photon. So you get two photons. And you have non-radiative processes that are Auger recombination. This is the absorption defects and many other things. You can excite phonons, lattice vibrations, for example, instead of emitting photons. So this is illustrated here. So there's a lot of ways to lose energy non-radiatively, and only one way to lose it radiatively. So it's actually not easy to do. Okay, so in order to generate light, you need first material with direct bandgap. And so I'm going to hope that many of you have taken semiconductor physics, so you know what I mean by it. Basically, it means that the bottom of the higher, like let's say conduction band and the top of valence band are lined up, so that momentum required for electron from here to recombine with the hole from here is zero. And the reason for that is that photons have zero energy, so you need to conserve in this process energy and momentum. And energy conservation is, you kill one electron in one hole, you lose energy, but you generate another photon, so you gain energy. So net energy balance is zero, but also momentum, because the momentum of photon is zero, more or less. It actually, the net, these electron and hole need to sit above one another. They shouldn't have any momentum. Materials that don't have direct bandgap are indirect bandgap materials. They are not very good emitters, and because they require phonon to participate in this process. Good emitters are gallium arsenide, indium phosphide, gallium nitride. Silicon is not good emitter. And often when we are making devices, we are not using one single medium. We are normally using so-called heterostructures to make quantum wells, for example. So here is an example of aluminum gallium arsenide heterostructure. That means you take two materials that have slightly different band gap. Okay, aluminum gallium arsenide has wider band gap than gallium arsenide. So when you put these together, conduction band is going to bend like this and valence band like that. So now you form this quantum well here. Okay, that all electrons that get injected into the conduction band eventually is going to end up in this well. So this allows you to increase probability of electrons and holes living in the same spatial region, okay? So that gives you a chance to higher recombination, and this gives you more light. So these quantum wells and then quantum dots as natural consequence are actually really important for light generation. In order for this to work, you need to pick materials that have appropriate arrangement of band gap, but also need to have the same lattice constant. And so often in literature, you find the graphs that look like this, that tells you energy gap of particular material is a function of lattice constant. And these materials are typically grown they're man-made using MOCVD or MBE processes. And this growth only can exist at kind of meaningful thicknesses if materials have the same lattice constant. And so therefore, for example, you see the aluminum gallium arsenide and gallium arsenide are pretty much lattice matched. So you can grow one on top of another. Okay, you cannot grow gallium arsenide on top of gallium phosphide, at least not very, very thick. But you can find kind of quaternaries like indium gallium arsenic phosphide, which is very useful in telecommunication emission, that actually can be grown on indium phosphide, for example. So this is actually quite interesting way of doing this. Okay, so this is the process of light generation, like basically have electron that gets trapped in quantum well, hole gets trapped in quantum well to recombine again and generate photon. And then often you grow multiple quantum wells, right? So to get more light more light you get if you have more quantum wells and inject more carriers basically inside them. If you just have material like this and send light to it, you're going to get light emission. That's how light emitting diodes work. But if I want to make a laser, I need to put an optical cavity or so around it. So either I can take medium that emits light and slap it on my ring resonator or my Fabry-Pero resonator, or I etch material that has gain, like 3,5 semiconductor, and put some mirrors on a facet, maybe distributed Bragg reflectors, for example, or make ring resonator out of this medium. So this is going to give me feedback, meaning once I get spontaneously emitted photon, this photon is going to be trapped in the cavity and stimulate emission of other photons. And then you get lasing, which is this curve here. Once you have enough gain, meaning you have enough photons in the cavity to overcome losses, intrinsic losses of the cavity. You have net gain and light, you basically start showing up. The way this works, you look at the output power of the laser for some current, there is no light for quite some time, and then eventually, for high enough current, you have enough carriers to generate enough photons, and these photons give you enough gain to overcome the losses of the cavity, and boom, you start lasing. Okay, so it's a very nonlinear process. So this is summarized here. You send electrons in, you pump this with electricity, this medium, you get inversion, you get electrons in excited state, they recombine, emit photons, photons get trapped in the cavity, stimulates emission of another photon, stimulates an emission of another photon. Eventually, this process has gain. More photons get stimulated and lost in one cycle, and that's when lasing happens. And I always show you these weak cells that are actually very popular these days. Very nice, very compact lasers. And there's making lasers is actually a whole art, and is very, very important, as CJ pointed out. Which brings me to CJ. Okay. 98 minutes, CJ. Giving 5 minutes delay, you're right on money. I think this would be you now. Oh, do you want to actually, yeah, let me stop sharing.
Okay, it's my turn now. So, yeah, Marco talked a lot about the kind of passive components and offered a lot of kind of mathematical kind of background to it, and then also started the conversation on kind of more conventional sources of light. Although lasers are not that conventional, given that they were invented like less long ago than you think, than most of us might think. And is part of the generation of devices that one might call quantum 1.0. But for quantum 2.0, where we're thinking about using quantum light for computing and that kind of thing, what we really want in general are single photon sources. And what is meant by a single photon source? Ideally, a single photon source would act like basically a flashlight that you kind of can just grab and then you click a button and then light comes out. And a very specific type of light needs to come out. It needs to come out as a single photon. It can't come out as laser light because laser light, if you look at the photon number, it's actually a superposition of photon numbers. It can't be like thermal light or basically just like light from like a bulb or whatever, because that also is a superposition of photon number states. What you want is a single photon coming out in the number state of n equals to 1. So this genre of single photon sources that we would need as a resource state for a photonic quantum networking is called a deterministic source, because every time you click, you're guaranteed to get one packet of light, one photon out. And under this class of sources, there are, as Marco alluded to earlier, things called quantum dots and things called color centers. Those are the two that I'll be focusing on today. But in general, broadly speaking, in order to have a deterministic quantum source, what you generally just need is like two energy levels that you can pump and then like wait for it. You can pump and then you can wait for it to decay, and then the photon that comes out will be kind of the energy difference between those two levels. So in general, it's kind of like what physical systems can we um, kind of massage into something that looks roughly like a two-level system. And I'll talk a little bit about how that is accomplished in a quantum dot, in a color center. But of course, there are a lot of other systems that can like had that can behave like as single photon emitters that you can use. And but then there are certain challenges with regards to getting to this deterministic source. So for a long time, and even now, a lot of the laboratory demonstrations of quantum optics actually rely on a different kind of single photon source called a probabilistic source. A probabilistic source is something like this. It's kind of like whenever you click a button, you only have some probability that you get your single photon out. And under those kinds of sources, they are it's mainly dominated by this class of sources called a heralded single photons, which are based on optical nonlinearities in certain types of specific transparent optical materials. So these are kind of sources that don't sound terribly useful at the current stage in abstract. Why would you ever want a source that kind of only works half the time? But in practice, actually, is the cheapest and most accessible for certain experiments, lab-based quantum optics experiments. Obviously not ideal. So between these two sources, there are certain figures of merit that they share for a single photon source that you want to put into, let's say, a quantum communications node. The figures of merit are as follows. The first one is a little fuzzy. I call it the quality of a single photon. And by that, that actually folds in a lot of things. In general, sometimes it's also referred as purity, that kind of thing. It actually folds in a lot of different concepts. One of the concepts it folds in is that photon really a single photon? So that is one characterization of purity, that quality of a single photon source that you often see. And then there's stuff like, oh, is it in this, whether or not it is entangled with the environment or with another photon. That's another indication of quality for a variety of reasons, depending on your application. And then the second thing is loss. And by loss, it means, well, how well can you actually get the single photon out and get it to the point where you can get it to, like, let's say your modulator or any of those devices that Marco talked about that you actually use to encode information into your photon. And finally, we have to think about whether these sources are kind of built out of kind of building blocks that are amenable to scaling. So that is the framework that I will kind of be talking about, these two broad classes of single photon sources that kind of are under development as part of like a photonic for quantum information applications. So the first type of deterministic single photon source that I would like to talk about, the first class of them are quantum dots. Quantum dots is basically, or rather, can in abstract be thought about as a sandwich of two different materials. There's a host material in dark purple here, and then a quantum dot material sandwich in between them. And what you're taking advantage of is that these two what you need to make sure of is that these two materials need to have different band gaps. And if you have different band gaps and you draw the band structure, kind of extracting out like the interface effects like band bending and that kind of thing, is that you can get this kind of band structure where if your quantum dot material has a narrower band gap, and then it can form a well on top and then a kind of barrier below. And what happens, like that's the host band gap, that's the quantum dot band gap. And what happens is that on top, you actually end up with a finite potential well. And finite potential wells, as is often kind of worked out in kind of in undergraduate quantum mechanics course, actually defines a set of energy levels within it. And then below, you have a finite potential barrier, which also defines a certain finite set of energy levels within it. And then you can excite, and then when it decays down, you get a photon that comes out. So using this like very, very rudimentary, very kind of simplified version of a quantum dot, we can actually understand a little bit of what we need them to look like in practice to function well in let's say on a photonic chip, a chip as a source of integrated photons. So let's think about the following. You have a finite potential well on top. You have a finite potential barrier below. For an ideal single quantum dot single photon emitter, what determines the wavelength of the emitted photons? Let's say we want something that travels well in an optical fiber, and so let's say at 1550 nanometers wavelength. The following options. Choose as many as you believe is correct. Let me put up a poll. The poll. Um, Whoop. That's not the right one, sorry. Uh, oops. Okay. Um, Oops. Oh, I suppose we missed a question in the polls. Uh, it's, hmm? No. Okay. Well, in that case, since this particular question, I must have missed it to while sending it to Brianna to kind of look at the polls, to implement the polls. Sorry about that. But yeah, I just want you to take a second to think about it. What are the factors here in all of the four things listed below that affect the wavelength of an emitted photon coming out of a quantum dot? Okay, sure. Since I can't see your poll results, I'll just kind of go through. So it turns out that if you think about the wavelength of an emitted photon, that actually is related to the energy of a photon, and it's related by hc over lambda. And the energy of the photon is defined by kind of the energy difference between the level that is dropping down from. So it's defined by the spacing between kind of these levels in a quantum dot. Now, as we all know, well, as some of us might know, or as you might know if kind of you've played around with any of the kind of applets or whatever for finite potential wells or potential barriers, the position of where these levels are actually is determined by how deep or how deep a well is, how high the barrier is, and also how wide in general your kind of potential well or barrier is. So in this case, the what determines the depth of the well or the height of the barrier are the relative band gaps of the host and quantum dot materials. So those two are important. And what determines the width of the potential, uh, uh, the well slash barrier is kind of the actual physical dimensions of your quantum dot. So which is defined by kind of how large kind of this quantum dot is physically in real space. Whereas the power of the excitation pulse that you use to get out your single photon isn't really important because you're talking about photon coming out. It has a well-defined um, energy defined by the energy levels, defined by the difference in the energy levels. So the answer is that all three factors, if you want a specific wavelength of emitted photons, are important. Now, okay. Now that I've talked about kind of schematically what it is, let's to think about what they look like. So this is an example, I believe, from a review paper on quantum dots, published like 6 years ago. So it's quite. So this scale bar is 1 micron. Quantum dots, it turns out, have to be really, 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 really small. And you kind of see these little hump here that's 50 nanometers. Um, so actually, in general, um, it's kind of hard to make. And in terms of the operating wavelengths that they generally are at, in terms of the quality of the single photons that the kind of indistinguishability and interference visibility that you can get out of, let's say, multiple quantum wells. This is a kind of a chart from a review paper quite a while back, so probably the metrics have improved. You see this crowding around like 800 to 900. So in the sense that a lot of the best quantum dots actually operate in this region of zero point 0.8 to 1 micron. If you remember, the telecommunications window is 1.3 to 1.55, which makes life a little bit difficult. We will have to operate at a shorter wavelength range if we want to use quantum dots as our single photon source. This can make life difficult for transmission, but actually it kind of makes life a little bit easier for detection because you can use silicon-based detectors to kind of detect these single photons. As for the materials that they're made of, as you can see, the host material here is gallium arsenide. The quantum dot material here is indium arsenide. So they tend to be relatively standard 3-5 semiconductors. And because of the feature sizes, these structures tend to often be grown epitaxially on a host substrate rather than like defined lithographically via etching. And generally that is kind of implemented by kind of having a specific kind of strain in the relative layers so that it kind of self-assembles into these like specific sizes. And then what people do is that they can define further structures on top of it to kind of extract them out. So quantum dots kind of are really useful that way. So in terms of figures of merit, if we think about the quality of a single photon, which one of the metrics is that are two photons coming out of a quantum dot, can they be the same? And can we interfere them? Because interference is often how we get kind of entanglement. Um, we can get near unity interference visibility in the best cases. So you can get true indistinguishable single photons. Uh, what about loss? Well, the best performing quantum dot emitters are not in the optical telecom band. So there will be some issues with loss if you're trying to use a fiber optics network, but the 800 to 1 micron, 800 especially if you're trying to do free space like just like ground to satellite stuff, it might be fine. Um, and finally, in terms of scaling, well, yeah, you can get all of the substrate wafers are commercially available. They might not be very large, but they are available. And while epitaxial growth is a little bit expensive, this tends to be fairly standard and industrialized for 3-5 semiconductors anyway. You just have to spend money on it for now. If it gets traction, I guess economies of scale might drive it cheaper. But so that's kind of the story I have for quantum dots. And so I would like to kind of turn the question back to you a little bit to kind of hear a little bit about your perspective on quantum dots, based on what kind of I've talked a little bit about. And I'll then provide a little bit of what my thoughts are in terms of the potential of quantum dots as a kind of potential like kind of cornerstone photon source in a quantum network. So I'll open up a poll and kind of the question here is, suppose you need to use a quantum dot single photon sources in your integrated photonics platform that you need to embed into a quantum communications network node. What would your biggest worry about like getting the sources to work? Would it be the loss? Are you worried about kind of the transparency windows of the materials? That like even when you do get the emitters out, it has like high propagation losses in the materials. Um, or would it be lost in the sense that you might have trouble sending them through an optical fiber or scaling where you have questions about the kind of wafer scale and like kind of manufacturing viability of it. So let me open up the poll. I'll give about a minute for this. Give it another 30 seconds. There's no right answer, by the way. I think these are all valid concerns that like kind of the community is always kind of evaluating and reevaluating when kind of on us on for different device levels, for different devices that people working on the device level, like Marco and I kind of come up with new devices, we kind of evaluate on how it fits into the bigger picture, whether it changes the game on like kind of one of the key metrics for that particular type of device, and then we compare it to other devices that can serve a similar function. And that's how kind of, and then eventually, that's how technology moves on and kind of converge in some sense. Okay. I By rambling, I ended up letting it run for slightly longer, but let's end poll and share results. So yeah, because I kind of guided the discussion a little bit through my presentation. A lot of y'all are kind of worried about whether or not quantum dot sources can get you photons that can be sent through optical fibers with low loss. And some of you are worried about, okay, whether or not wafer scale fabrication really produces kind of, let's say, arrays of these quantum dots that can be indistinguishable, maybe possibly shaped by the kind of figure that I chose to show as an example, where you can definitely see a lot of dimensional variation in the dots that on the substrate. So yeah. So generally speaking, actually, for me, I actually tend to think that scaling is actually my biggest question on in terms of the potential quantum dots for a number of reasons. The main reason is actually the critical dimensions of these are fairly small, and a lot of the growth process seems, at least to me, to be kind of inherently random. It depends on um, kind of engineering the right strains so that the material kind of forms these the material and preferentially forms these humps. You can't really control where they are. There will be some spread in the size. Um, in some sense, that is the thing that I have biggest questions about as somebody who kind of works adjacent to these sources. But in terms of the other two aspects, transparency windows, I'm not too worried about for 3.5 materials, actually. There have been a lot of work done to kind of push down on the propagation losses of passive photonic components fabricated on these. It turns out that by controlling the material composition really, really carefully, you can get to pretty low loss, material loss inside a waveguide in these 3.5 materials that host these quantum dots. And also in terms of where the wavelengths at which these quantum dots operate, there is a good deal of research being done, and like I think you can definitely find some telecom examples, although they just might not be as mature yet. Of course. So that's kind of my discussion on quantum dots. And eventually you'll get these slides, and I'll definitely recommend checking out some of the review papers that are linked here to kind of catch up on how quantum dots are doing these days. Well, but aside from quantum dots, right, which are completely artificial kind of atom-like things, like two level kind of structures that can get you single photons. You can also get like atom-like things from um, let's say from diamond. Um, These are framed in terms of spin qubits, but and that is true. You can use them as qubits because of various reasons. But if you don't use them as qubits as or as memories, you can actually abstract a lot of this away and say, okay, because that a diamond, because when you have a diamond and you have a kind of regular lattice of carbons and you have certain types of defects, like a nitrogen vacancy or a silicon vacancy, a defect exists in the band structure and therefore forms kind of like a little two-level thing. And then by going between those two levels, you can get a single photon out that way. So for if you look at if you're familiar with the Center for Quantum Networks, a lot of the kind of the technology that a lot of our work is based around is actually the Silicon Vacancy Center in Diamond, mostly because we want to use it as a memory. So there are a few things that are good about the silicon vacancy, which is it has an optically accessible spin transition. It has a relatively long coherence time, and then kind of um, you kind of are, because of inversion symmetry, you kind of are immune to like a lot of the fluctuations kind of in the ambient like ambient environment, kind of le electrical electric field environment. So all these levels don't fluctuate that much. So these are mostly important for kind of using it as a memory. But if you look at the electronic structure, you have these ABCD lines, or rather you have four levels, but what you actually care about is kind of a large optical splitting that's about 737 nanometers. And what is used to tune generally the color of the photon that comes out of these silicon vacancies is strain, because it's by inversion symmetry, you can't tune it electronically. You use strain to kind of tune them a little bit, and that can get you like not that much tuning in practice, but just enough. And so in terms of diamond photonics based on silicon vacancy centers, or for diamond photonics, they are built around like having silicon vacancies centers as a memory or a source. Um, what um, what we have been able to what folks in the community have been able to do are a lot of these kind of impressive things that are mainly for uh kind of repeaters and memory enhanced quantum communication. But over here, if we think about it as a source, what actually is important here is just that you have a good way of coupling them out so that you have these vacancy center emitting in, let's say, a cavity. You can actually extract it efficiently out of this high index contrast waveguide using a specific type of adiabatic kind of tapered fiber coupling, um, and um, and and you can actually pattern structures on it to resonantly enhance certain to enhance emission, and also to kind of you can deterministically kind of implant them into where um, the devices are located, either by masking it out or a number of different ways. And so the key to this actually was is the key to getting like vacancy centers working with like in kind of a nanophotonic devices and building it around it is actually a fabrication development. Basically, diamond actually, if you think about semiconductor fabrication, is not exactly a material that like is commonly used. So kind of etching it and kind of processing it is a little bit, especially at kind of dimensions for photonic crystal cavities like these one, um, it's quite challenging. And also, you don't really have thin films of diamond available, so you actually, in order to form a waveguide that in order to form a like waveguide, you generally want to suspend it from the bulk instead of relying on like a thin layer of diamond on a different index material to provide confinement in the vertical direction. So a lot of pioneering work has been about like developing, let's say, angled etches to get out to suspend out waveguide structures so that there's confinement in the vertical direction, and then working out the fabrication process flow for getting like good smooth sidewalls for high Q factors, so that the cavities are good, and also being able to pattern these holes that for your photonic crystals. And there's also other, but as you might notice, this triangular profile maybe is not like, that great to work with. Most of the waveguides that we want, the ideal waveguide that we often kind of sketch out is a something rectangular that just makes it like a lot more symmetrical and easier to simulate for various reasons. There's also quasi-isotropic etches developed, and using this, you can access a different design space, and then you not only can you do photonic devices where you can confine photons, you can do phononic crystals in these in diamond. And phononic crystals are important because um, as I mentioned before, even though silicon vacancies are protected by inversion symmetry against like the kind of elect fluctuations in the electric field in the environment. Um, it's sensitive to strain, and so kind of having a phononic crystal to shield it against kind of mechanical kind of phonon interactions is actually quite important for the quality of these silicon vacancy centers for use mainly as memories. So as a source, basically it's generally fine. So kind of a little bit more about fabrication processes since we didn't talk a ton about fabrication, but at the core of a lot of these integrated photonics is kind of fabrication processes that basically derive from traditional semiconductor fabrication. And in general, the steps are kind of you define a mask to define a structure, and then you can and then basically you use a plasma or some kind of chemical to kind of etch away the material. So, in macro fabrication, or like you think of a CNC mill as a blade that comes in and cuts material away. Well, in this case, because the feature sizes are so small, it's generally a plasma. And the way that you define where it's etching is by using a mask that like is resistant to it. So all this is kind of developed in traditional semiconductor fabrication for fabricating, let's say, like transistors in the chips that go in your computer and that kind of thing. And then comes a little bit of an interesting part where um, that is specific to this desire to make suspended diamond structures, because for a really long time you could only get bulk diamond. You actually do material deposition, and material deposition is something that you do fairly commonly. A lot of materials, like you deposit oxides such as silica. We call these cladding. Often for integrated photonics, you deposit claddings or like hard mask materials. This particular type of deposition is called atomic layer deposition, compared to other types of deposition techniques that are out there, that are, let's say, like whether physical or chemical, it tends to be more conformal. And that's how and for diamond, it was really important so that to get it extremely conformal so that it coats all of the sidewalls. And then by making use of a very anisotropic etch, you selectively just break through the top surfaces. So and then you do an isotropic etch. So this is the process for the isotropic etch. And then you dunk it in an isotropic etch, and then it'll undercut from this surface down, and then it'll break through over here, and then it'll start etching upwards. And then eventually you're left with this kind of beam of diamond, still with mask on top, with the kind of side walls protected because of this deposit and isotropically deposited layer. And then after that, you can clean it with, let's say, hydrofluoric acid or whatever material, depending on your mask material, to get these suspended beams. So you can kind of see kind of the process in scanning electron micrographs here. And what I really want to kind of draw your attention to is that this is the first fab diagram, I think, in this workshop so far. A lot of the most of the kind of techniques that we use to make these integrated photonics devices, it's kind of just a remix of like etching, masking, and depositing things and then removing masks. And then we can play around a lot with geometries by controlling the whether or not the etches or depositions are directional or not. So that's kind of something to keep in mind. And kind of in general, in terms of scaling, as the closer your material is to what is processed, for let's say making integrated electronic circuits, the kind of faster you can scale kind of the complexity of your devices. So let's say for silicon, it actually you can scale this complexity of devices quite quickly because a lot of etches for silicon and let's say silicon dioxide have decades of research behind them. Many of the parameters are optimized, let's say the sidewall verticality, whereas for kind of for diamond, which kind of is a newer but now not so new anymore material, you are actually dealing with trying to develop etches kind of on to from scratch. And this is actually a large part of kind of research in, let's say, nanophotonics, where if you have a material with kind of interesting properties that you want to pattern to make resonators or specific waveguides in it, a large part is figuring out what etches these materials and what quality of etches you can get and whether that actually gives you good photonic devices. So this was true for diamond and it was true for lithium niobate. It's true for essentially all of the materials that Marco talked about earlier. It's something that's not talked about very much, but because it's the actual process of doing fabrication in a laboratory setting is much like cooking, but it's actually kind of enabling technologies. Yeah, so that's kind of our collective spiel on a fabrication. Now, so a lot of people, graduate students and researchers have spent a lot of blood, sweat, and tears developing this method of creating waveguides in bulk diamond, let's say, because it kind of you can have these you can not only pattern kind of nanophotonic structures to enhance emission on it and kind of deterministically place kind of where your emitters are. Because it was on bulk, you have to do this crazy suspension situation. Now, what comes as a game changer and has been brewing for the last, well, more than a decade is the prospect of diamond thin films, which if you saw the diagrams of, let's say, thin film lithium niobate that Marco showed earlier, the vertical confinement is provided not by etching down, not by suspending a beam from the bulk, as is the case here. You just have a thin film of diamond, just like you have a thin film of lithium niobate or silicon nitride, any number of those materials that you can buy on a different index material, so you're getting index contrast that way. So that has been kind of the dream for a little bit, and there were a number of demonstrations of various devices, but there are also a number of challenges because various ways of fabricating these diamond films, often you're dealing with kind of really silly issues that, not silly, but like the simplest thing that ends up being quite complex. It's kind of like you're trying to, let's say, put a thin film on a surface though. So like many of you have like applied screen protectors on your phone or whatever, and you have a bubble trapped underneath, and suddenly you have unevenness on your substrate, and then you have fringes and that kind of thing. So a lot of work has gone into kind of being able to transfer or grow and transfer these high quality diamond films on a different substrate so that you can make integrated uh, photonic devices on them in a more traditional manner without like additional suspension steps that involve like long atomic layer depositions, etc. So, um, so one of the ways that so so just to give a little bit more context to kind of this figure over here, um, one of the ways that these diamond films are made is kind of Wait, actually. Mm, yeah. Uh, hmm. Marco, actually, could you
You
chime in
can
on
just
this
skip this one.
particular
Thank you.
figure? I
So
think this is considered
I added
a
this
late
in the last
point.
minute. Just skip it in the interest
Yeah.
of time.
Yeah. Yeah.
It is
But
yeah.
yeah, but the core message here is making diamond thin film has been and is still very difficult. And just the fact that you're trying to make these thin films and like transfer them actually involves a lot of development and research actually. But in the end, you can get really nice structures in diamond, 1D photonic crystals, 2D photonic crystals, really long tapers for good coupling. But in any case, um,
You can
I
skip that too. I was just showing
am
the
also going to skip a bunch of stuff
yeah,
about how we use these
yeah.
diamond photonic well, how we work with these diamond photonic single photon sources because what the message of these past couple of slides here is that these single photon sources actually depending on the environment that they're embedded in they don't always emit at the same wavelength, so you actually have to tune them back, and you can't tune them a ton just by like applying strain to, let's say, your beams that you fabricate in diamond. You sometimes have to use external. So this is kind of showing kind of distribution of like the distribution of wavelengths that you kind of have emitters at. And then you actually have to use external components, active components in that like to kind of shift these photons together so you can use them for interference and such. So there are a number of ways you can do that. You can do it with this technique called frequency shearing, which essentially uses an electro-optic phase modulator that Marco talked about before to kind of shift the pulse of light. And then there are different ways to kind of just combine them together. And then because they also emit at 737 nanometers, for that is still that similar to quantum dots is in the range where it's like really, really hard to send efficiently over fibers. I think the metric is like 5 dB per kilometer versus zero point 0.3 or some dB per kilometer in telecom. You actually want to be able to shift these frequencies to telecommunications wavelength bands using using something called quantum frequency conversion, which really is just a nonlinear crystal that kind of uses a separate laser source, let's say, to kind of subtracts the energy of the photons from that laser source from the energy of the photon emitted by SIV to create a lower energy, so longer wavelength photon that is compatible with telecommunications wavelengths. So this is my work, which probably is why Marco added it, but we've spent a long time on these. I have spent quite a fair bit of time on these diamond kind of single photon sources. But the story essentially is quite similar to QDs, where you have some issues with getting it at the right wavelength. Your fabrication, yeah, you can place them a little bit more deterministically, but until very recently, where thin film kind of technologies have become more mature, patterning devices around it has been a little bit tough. So for a number of reasons, these kind of deterministic atom-like um, single photon sources are kind of not commonly used when all you want to do is kind of demonstrate like certain quantum optic phenomena in quantum optics, such as Hall-Mandel interference, or do like proof of principle demonstrations of like, I don't know, like BB84, or do a Bell's inequality violation in polarization space. What most labs actually end up having to do is to rely on these probabilistic single photon sources, which is kind of where my specific background is. And just to sweep through it very, very, very slowly, a probabilistic single photon source is made by picking a material with either second order or third order optical nonlinearity. And by optical nonlinearity, I mean that if a material is linear, what it means is that if you have light at a particular frequency going into a material, it will never generate other frequencies just because of Fourier transforms and that kind of thing. Um, and let's say you have two frequencies going in, the same two frequencies will come out maybe at different attenuations with different phases depending on the dispersion of the material. But for in a linear material, you will never generate new frequency components. However, if you have a second order or third order optical nonlinearity, you insert kind of a frequency, a light at a particular frequency, you can get different frequencies out. And this is what this diagram shows. It actually shows a strong beam, pump beam being injected into a material. This light, let's say, is blue, so a very short wavelength, very high energy. And what happens is that a parametric nonlinear process can happen, and a pair of photons that satisfies energy conservations. So there are two photons generated, energy generated where the total energy of these two photons added together is equal to the energy of a single photon at the original pump frequency can be generated, so pairs. And not only that, they are momentum conserved. So schematically, this is represented by like, like conservation of momentum where they have to go in opposite directions, but in reality it's a little bit more complicated than that because you're actually thinking about wave vectors and that kind of thing. And the critical point here is that they're always generated in pairs, and what you do then is that, okay, a you have a material that when you pump with a strong pump beam sometimes generate photon pairs. And so what do you do? What you want is a single photon, not a photon pair. What you do, well, you can separate this pair of photons into two different, often spatial modes, and then you slap a detector on one channel. And then you say, okay, I know they are always generated in pairs. So if I detect a photon in this channel on the lower side, the orange one, then on the other photon that is still traveling in whatever channel that is, I know for sure that I have something, a single photon here that I can use, let's say, to do an operation on. So what we call this is that and then what we use is that we can either use the detector to herald we can just keep doing a particular operation in our node, like let's say in our node that in our in keep doing a particular operation, and we only say it succeeded when we know that there's a photon that actually was being operated on in the other channel by looking for a heralding click on this detector. Or you can, if you have fast enough electronics and routing and memories and that kind of thing, you can wait for the detector to click and then decide to send a photon from this channel that was generated at the same time as the pair photon to be processed, right? So this is the schematic for like a probabilistic single photon source. Now, uh, yes. Exactly. So sorry, there's a repeated slide. And then so here's a question for you. Why do you think this type of source is actually probabilistic? Right? Which step is it actually probabilistic in? And I'll start the Zoom poll, and while we wait for the Zoom poll to wait, hold on. Okay. Well, maybe let's just think about it a little bit, and because I think the particular question was missed again. Sorry, Brianna. Um, and then we can, yeah. So actually, um, none of these steps kind of I have currently listed mention like anything about probability or things that are happening probabilistically. But let me let me just point out that, let me just highlight which part is probabilistic, and that will inform kind of the later discussion. So the part that is probabilistic in this entire process, right, is actually this parametric nonlinear process, where the initial pump light actually splits into a pair of daughter photons. This actually occurs due to like vacuum fluctuations. And generally you can only and kind of this part you can get from like perturbation theory, which gives you a probability that like a pair of photons is generated given like a certain Hamiltonian acting on like vacuum states. And so kind of if and to give it kind of a more kind of mathematical treatment, let's consider this second order nonlinear optics process where you have a strong pump, so we treat it semi-classically, interacting in a second order nonlinear in the medium with second order nonlinearity. You actually have a Hamiltonian of this form, and initially, the state, right, in this medium is vacuum, no photons at all. This is your initial state. And then after propagating through the medium, time evolution via this Hamiltonian, what you end up is this particular state, which kind of we can do a lot of math and rearrange into this form and into kind of in terms of pairs consisting of these like where written in terms of like the photon number states, right? And then the probability of there being n photons in each mode is given by this equation. And so a few observations and notes here. This state generally has a name. If you've been in the quantum space and are thinking about other applications like sensing or that kind of thing, or metrology, you probably have heard of a squeeze state or vacuum state. That's this is actually the general form that it takes. And the squeezing, and then this parameter R here is a function of interaction strength, zeta, and interaction length, which also, you know, propagating through a given length means that you're propagating through a given number of time. And the interaction strength depends on pump power, effective nonlinear coefficient, and the way that the optical modes are confined in the medium in a kind of a in yeah yeah that gives you kind of different values in this R. And so far it is, and also you can observe that actually it's not obvious where these energy and momentum conservation conditions come from if we think about it in this framework. But I'll just say that it actually I'll just say that it's because in this particular process is highly non-off resonant, so actually you're um not transferring any energy or momentum to the material itself. The initial light pump light doesn't transfer any energy or momentum to the material, and so therefore energy and momentum conservation must be big. And then and so if we look a little harder focus a little bit harder into the kind of state that we get out at the end of the propagation through the medium, and we look at the probability of n photons being in each mode, we realize that n actually is summed to infinity, right? So it starts from 0 to infinity. And actually, we can plot out the coefficients here. We can break it down to each pair of n terms, and then we can plot it out. And then we can plot it out like this. So we can plot out the probability that actually propagating this for this length through the material, actually nothing happens. You have n equals to 0, just like before. And so you can plot it out here. And then you can just like plug in as a function of R, the squeezing parameter. And then you can also plot it out for 1, which gives us the useful case in most cases of heralded single photon sources, where you're guaranteed one photon in each channel, right? This is the orange curve. But actually, as you will find that as you ramp up R, you actually, the coefficients in the higher order terms actually also start getting very large. So there is a probability that instead of getting a pair of one photon in each channel, you can get a pair of two photons in each channel, a pair of three photons in each channel. So these three curves actually describe, okay, the probability of nothing happening, which, as you can see, is for a lot of the time, actually. For most cases, the probability of nothing happening is very high, so you get no photons coming out. But then you get to your useful case, it actually has a turning point that like dips down here, but it has a maximum here. And the reason it dips down here is because more multi-pairs are being generated, so this green curve starts going up, right? So basically, in words, you have about greater than 50% probability of returning a vacuum state, so about here, until R is greater than 0.88, so quite high squeezing. But then you actually start getting a probability of more than one photon in each mode. So like multi-pairs at a rather modest R. So you actually get a high probability of multi-pairs at R much less than 0.88, like over here. So now here's the question. So given that R, as we mentioned before, depends on the interaction strength, is given by the interaction strength, which depends on pump power, effective nonlinear coefficient, and mode overlap in the waveguide or in the material of the optical fields in the material. Is there an optimal pump power to operate at? And for generating heralding photon pairs to be used as part of a heralded single photon source, what would be the optimal R to operate at? And if there is a poll set up correctly for this, I will bring it up. And if not, let's just spend a little bit of time thinking about this. Hmm. So there is a poll for the first question, but not necessarily the second part. So yes. So, uh, yeah, and to answer the question, let's it might be helpful to think about the kind of second question first of what is the optimal R to operate at? All right, that's 2 minutes, and we've got maybe a 50% response. Okay, great. Most of you said yes, and there are three of you that said no. So, To answer this question, I'll take the scenic route and work backwards from the second question, which is there an optimal squeezing parameter R to operate at? Um, and at the end of the day, it is this R parameter that's important, right? Because that determines you basically what you want to do is actually you want to dial in your R parameter so that you want to operate at a pump power that gives you a specific R. So is there an optimal R to operate at? Well, I gave you three options. And actually, this is a little bit of a trick question because only the first option is kind of wrong. And whether or not you want the second one or the third one actually depends on what you use to detect those photons in your system. So let's say whatever you build, yeah. So let's say so in the first option is wrong because when you say okay the optimal R what is when the probability of more than one photon in each mode is minimized. You look at the green curve and you'll see okay actually this green curve doesn't turn around. If you want to minimize this you actually want R equals to 0 and unfortunately at 0 the probability of your useful pairs, which is one photon in each channel, is also 0. So obviously the first one is wrong. However, the question of whether you want to maximize the probability of exactly one photon in each mode, or whether you want to kind of take a balance of you want take a balance of you want there to be a balance of multi-pairs and single pairs, that your useful resource state is a little bit subtle. So in general, you can operate here at the turning point. So option 2 is right if and only if your detectors are photon number resolving. So you can just discard all of these multi-photon events and say, okay, these actually aren't generating the resource states that I need for, let's say, my communication application or for my computation. However, if your detectors are not photon number resolving, you have one click, regardless of whether you're generating one pair or multiple pairs. And the multiple pairs are not useful. So actually that creates a lot of noise where you're actually maybe doing an operation on a resource state that is not actually the state that you want. So actually what you would want to look at is the ratio, but the probability of a click on your non-photon number resolving detector that click is actually corresponds to only a single pair. And so it's plotted over here. And you can see that unfortunately this thing also doesn't have a maxima. It actually just keeps dropping. But if you operate here, you go back to the same problem where the probability of even getting single pairs is really low. So in reality, you want to operate somewhere here where most of your photons are not multi-pairs, but you're kind of operating in a very restricted region. Um, and so, given that, whether or not what the optimal R is squeezing parameter it is to operate a probabilistic single photon source is, kind of has it depends on the detector kind of answer. It's actually hard to say that there is a optimal pump power to operate at. So that is reason one that it's actually hard to say. Like, it's hard you can't actually claim that, okay, for a given source, I need to operate at a particular pump power. The second reason is your pump power actually, um, your R actually depends on a whole deal of other parameters, such as the effective nonlinear coefficient of the material itself, and also the mode overlap in the material. So for the mode overlap, you can think about it as power density, and then the effective nonlinear coefficient is just how strong the process, how likely the process is to inherently happen. And you can actually, for materials that have low nonlinear coefficients, you can actually crank up the power up to like, as long as you don't break the material to compensate for low nonlinear coefficients, um, while trading off while trading off like kind of like wall plug power, you just need a bigger laser. Or if you have a really good material that has a high nonlinear coefficient, let's say, I don't know, some 3.5 materials or lithium niobate, you can drop the power quite a lot. And if you have a low pump power requirement, then that opens up a lot of opportunities for pumping this with, let's say, smaller, lower power lasers that are easier to make in a small form factor. Although due to some DARPA programs recently, there are some pretty high power lasers that on chip that people have been able to make using a variety of platforms. But in the end, all this to say, whether the answer to whether there's an optimal pump power to operate at for a probabilistic single photon pair source is actually no, or rather it depends. So many of you, some of you have clocked that, but I think a lot of the time we always think it in terms of power, but because of this this is a probabilistic process, and like the probabilities of your useful kind of cases and kind of fluctuates with your pump power in kind of a non-intuitive way. A lot of the time we think that there's an optimal pump power, but actually we can keep cranking it up higher and kind of never actually find an optimal point. It's not convex, as it were. So that's kind of my little spiel on probabilistic single photon sources. And this is actually why I made Marco talk about the lasers, even though he wanted to skip it. It's because these probabilistic single photon pair sources actually relies on the fact that A, nonlinear optical materials are not that hard to find, and B, we now know how to make lasers pretty well, so we can pump these materials. So if you can afford, like, let's say a block of nonlinear material and like a small like laser, you can actually set this up in like even an undergraduate lab quite easily, and that opens up a lot of opportunities for doing things like Bell's inequality breaking or like Homo-Mandel interference in like a laboratory setting for low cost and um yeah. This is what I have on single photon pairs. So based on what I've described, it almost sounds like these probabilistic single photon sources are worse in every possible way compared to deterministic ones, right? You can never there isn't really even a clear way to operate them where you get your useful resource states all of the time. You have to like always trade off getting some noise in terms of non-useful resource states in the terms of multi-pairs. And if you try to keep a large fraction of your if detector events as useful resource states, you're actually going to be waiting forever for an event to happen because you're operating over here where the probability of a generation of a photon pair is really low. So is this true? Well, you know, in principle, kind of yes. But in practice, maybe not, because it turns out that a lot of there are some distinct advantages compared to atom-like deterministic sources that has made it kind of the cornerstone of a lot of the larger scale demonstrations of like quantum computing or information work that or quantum optics demonstrations that people have been able to do. So this is some work done in China involving like basically a ton of photon pair sources and interfering them together. And the reason these kinds of experiments are implemented that way is because these sources, like I alluded to, are actually relatively cheap to set up. I paid to align many of those, obviously, but the other thing is that they're also much more versatile than atom-like deterministic sources in terms of where it emits and the bandwidth. You can generally kind of tune those by choosing your pump laser appropriately. As long as your pump laser, as long as you basically can define what you want your heralding photons wavelengths to be and what your heralded photons wavelengths to be. Most of the time, people want it to be both in telecom. And then you add the energies of those photons together, and then that says, okay, you want you want a particular laser wavelength. So for example, let's say I want a I want my heralding photon at 1550 and I want my heralded photon to also be at 1550. That if you add the energies and compute the wavelength, it's just you just need a laser at the second harmonic, which is 775 nanometers, which you can just buy. So it tends to be fairly convenient. And not only that, you can also do things like, okay, instead of having my two photons be the same wavelength, you can do things like, okay, I want to detect my heralding photon using a silicon detector, which doesn't need cryogenic operation, which, as I will talk about later. How should I set up my source? Well, a you can just choose a wavelength for your heralding photon, let's say 800, that is detectable by silicon APDs, and then you choose your heralded photon that you actually want to send over a link or whatever to be in telecommunications wavelength to, let's say, be fed 1550, and then you do some math, and then you realize, okay, I need to pump it in kind of in the visible close to UV, and then you find yourself a laser there, and then you pump it. And then you can get these combinations of wavelengths. This is not something you can do with atom-like deterministic sources. In those sources, your energy levels essentially set what emission wavelength you have. You have very, very little flexibility. But these probabilistic sources um, don't have these issues. And for most part, you can operate these things at room temperature and not run into kind of these broadening issues that you start facing with kind of sources with like different levels with based on kind of atom-like um, defects or artificial atoms. And also, nominally, it's kind of easier maybe to make large arrays of identical sources because at the end of the day, you just need like blocks of nonlinear material and you kind of split a pump laser across many blocks of nonlinear material. And well, that's in bulk, but in integrated photonics, well, the whole thing is that you can route light really easily using waveguides and such. So you can imagine having a pump going into a chip and then all of this like free space setup that is depicted here, you can do a fan out, and then you just have rows and rows of waveguides, and then suddenly you can have like 10 of the 10 identical like probabilistic single photon sources. In the ideal case, right? There are asterisks, obviously. And so more on wavelength and bandwidth versatility. A large part of it also I alluded to is part of it is the fact that the constraints on what wavelengths the photons are generated are fairly loose. But another part is also, even within that, you can also choose from a wide variety of nonlinear materials to get you these photon pairs. You can use second order nonlinear materials like beta barium borate, potassium titanyl phosphate, lithium niobate. There are other ones, depending on your application, whether you have specific requirements on the dispersion of the single photons that you generate, photon pairs that you generate, what power that you plan to pump it with, that kind of thing. Or if you don't want to use a pump laser that's really far away from where your photon pair is generated and you're okay with kind of doing some hardcore filtering, you can even use a third order nonlinear optical process where kind of you can pump at a wavelength that's in between the wavelength of the two photons that you're trying to generate. And basically, two of those photons then combine and then split into two dotted photons. And that is accessible in a much larger range of materials, including some of the leading materials for low loss passive routing like silica and silicon nitride. And this is basically a restatement of energy conservation. The momentum conservation condition is a little bit more tricky. In bulk, you can use different propagation directions of your generated photons relative to your pump photon to satisfy the momentum conservation property for your process. But there are also ways to engineer gratings to introduce an artificial grading momentum to compensate for any momentum mismatches, let's say in a linear device, like in a collinear waveguide or that kind of thing. And basically what you can think of that is you are introducing a periodically inverting you are periodically inverting the sign of your nonlinear coefficient, which mediates this nonlinear conversion. And if you do a Fourier transform of that, that's going to give you a frequency at e to the I 2 pi over the grading period. And that can act as an artificial momentum kind of to grading momentum to cancel out whatever initial kind of delta K there is. And this can be done in a large class of materials, including lithium niobate. These materials are called ferroelectric materials, where the sign of the second order nonlinear coefficient can be periodically inverted just by applying an electric field to the material. And this is called periodic polling. It was developed initially for bulk crystals, but is actually commonly used for waveguides, either large waveguides with like confinements of tens of microns that you can fabricate by dicing or using pulse lasers, or in the kind of etched waveguides that we do in our group on thin film lithium niobate. Now, a sidebar on this is that because of a weird quirk of this energy and momentum conservation condition on photon pair generation, you can actually get correlations between the signal and Euler photons. So the two photons there are the pair of photons, the two photons that are generated, they are actually entangled in general in the spectral temporal degree of freedom. And I think basically, you can think about it as this. If you plot out the frequency of the of one of your photons, and then you plot out the frequency of the other photon, by the energy conservation principle, the line along which the process is allowed is always along the anti-diagonal direction, and then orthogonal to that is determined by the bandwidth of your pump. It's always going to be anti-diagonal. But then because of material dispersion, your phase matching can actually take on different slopes. And depending on how long your interaction length is, it can also have different widths. And so when you multiply it out, the probability of, let's say, a photon of one of your photons, the probabilities that you measure your generated photon at the joint probability that you measure uh, your two photons at a particular pair of frequencies can be correlated. So in the bottom plot, basically, if you measure the frequency of one photon, it actually almost gives you a lot of information about the frequency of the other photon. Whereas in the top plot, because there's no tilt to kind of the spectral distribution of the two photons, you get very little information about let's say uh, the heralded photon if you measure the frequency of the heralding photon. So this can be important for certain reasons, for some reasons, because if you don't have a spectrally resolving photon detector, it actually does a partial trace along the heralding photon when you detect it, and then it basically for states where you get a lot of information about the frequency of your um heralded photon, you actually collapse it into a mixed state, which ends up being like relatively not useful for many quantum communications and especially computing applications. So for a lot of cases, including kind of the zero added loss uh 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 kind of uh kind of architecture that the Center for Quantum Networks uses, we actually want these photons to be engineered so that they have relatively independent distributions of uh, uh, frequency in the heralded and the heralding photon. So Now, with that out of the way, let's review these probabilistic single photons a little bit. Let's talk about figures of merit. You want, in terms of quality of a single photon, it really depends on where you choose your operating point. There is a trade-off between purity, which in this case you can think about the fraction of non-vacuum events that are actually in a useful resource state, aka single photon pairs. If you're using click no click detectors or non-photon resolving detectors. Um, and in terms of to get spectral purity where your heralded photon is projected into a pure quantum state, you actually need to filter. You very often need to filter or do state engineering to get non-correlated spectral distributions for your two photons generated. In terms of loss, because you're using these nonlinear optics material. The materials that you use are generally transparent. So that is negligible. Propagation loss tends to be negligible. It's also kind of trivial to generate photons in the optical telecom band, which is compatible with low loss transmission in optical fibers. You just kind of have to choose the right pump wavelength and deciding on what wavelength you want to herald on. And finally, in terms of scaling, well, you have your heroic free space demos involving large arrays of sources. Well, okay, but then the topic of this particular seminar talk is integrated photonics platform. So what's the state of these probabilistic single photons in bulk? Well, it turns out that there are quite a lot of efforts to put these sources onto integrated photonics platforms, and you can find it in like 3.5, most of the popular kind of integrated photonics materials that people have explored. You have it in 3.5, in aluminum nitride, silicon, lithium niobate, silicon nitride. And the reason is quite simple, is because the actual structure that you use to generate these kind of photon pairs is actually quite simple. You just need to propagate it through a material with nonlinearity. So you just make a waveguide, which is what we're doing in any case when we make integrated photonics devices. And if you really want to get fancy with it, you can make a resonator, like Marco talked about before, to enhance certain effects and to shape the spectrum of the generated photons even more by selectively enhancing it, like in these examples, right? And this can be done in such a wide range of materials because this kind of process uh, is you can there is a way to kind of have this kind of process happen in kind of most materials. So because most materials have a chi3, have a reasonably high has a reasonable high chi3. So if you can tolerate some additional like pump power, like higher pump power requirements and kind of tougher, more stringent filtering requirements, you can actually do it in silicon nitride and silicon, which are more mature platforms. Um, and well, in terms of and so in general, like you can have these probabilistic single photon pairs have been demonstrated in basically most of the platforms that you care about. And I guess if they haven't, it's probably just a matter of measuring it. And and like in terms of high quality in the sense that the photon pairs, you can interfere heralded single photons generated from multiple sources with high visibility. They're kind of the highest quality and spontaneous full-wave mixing sources based on silica and silicon. And most of these demos, because most of these applications are targeted towards quantum communications and like optical links, have been demonstrated in telecom band, unlike, let's say, like some of the other sources we talked about. So, so recalling the advantages compared to atom-like deterministic sources, it is easier. let's consider the asterisk when it comes to these kinds of making large arrays of these kinds of sources for a few different configurations. Where does that asterisk come from? Well, one of the reasons there's a big asterisk on whether we can make large arrays of identical sources and why the kind of leading demonstration is kind of on a kind of silica on silicon as opposed to like some of these resonator based structures is because, well, if you shape the generation of your if you shape where your photon pairs are generated by selectively enhancing certain wavelength lines using a resonator, actually the whether or not two separate sources are identical relies heavily on an alignment of resonances at pump signal and idler. This actually ends up being quite difficult to target this deterministically, mostly because of material dispersion. Um, and there are efforts towards like, making, let's say, Fabry-Perot cavities using like two different periods so you can deterministically place where kind of band gaps are, and so deterministically determine so you can select which wavelength range select specifically which wavelengths are resonant. But those tend to be very vulnerable to the fabrication tolerances, which is also the origin of why, let's say you make two identical ring resonators next to each other on a chip, they actually have slightly detuned resonances. But in some sense, these can be compensated by tuning, thermal tuning. It does pose a more stringent fabrication constraints and kind of controls and complicate the control mechanisms that we need to operate such sources. And next, the other asterisk comes from the fact that actually moving these probabilistic sources onto integrated photonics, while it has certain advantages in terms of like the raw power needed to pump this process, um, the sub-wavelength confinement on most integrated photonics platforms exacerbates the sensitivity to waveguide geometry. And the reason for that is because when you have sub-wavelength confinement, your waveguide actually, because of the confinement, the propagation constants at a particular wavelength for a particular spatial mode starts to change, deviate from material dispersion. So kind of that will shift where it's phase matched around. So where your device's phase match can be very, very sensitive, which kind of people have explored, especially in for that people have explored in great detail. And there are ways around it by like making your waveguides thicker so that you're confining it less tightly, but that kind of sacrifices, let's say, bending radii and a number of other good properties of and routing density that we like in an integrated photonics platform. So and a lot of the material platforms that support the more efficient and easier to filter version, which is spontaneous parametric down conversion, are less mature compared to like, let's say, silicon or silicon nitride. But of course, compared to, let's say, like making integrated photonics and like, I don't know, like diamond or whatever, uh, obviously it's a little ahead, but in some sense that is not making monolithic integrated photonics on diamond is not really a viable path that anyone is really considering, I think. So, uh, just to summarize again, for probabilistic single photon sources in general, here are the figures of merit compared to that you can keep in mind to compare against other types of sources that you may come across as you read about how we generate resource states for quantum information. And finally, how do we get rid of how do we get rid of the probabilistic part of the probabilistic pair production? It seems like in general easier to get the wavelengths that we want, and also to kind of fabricate um, than these atom-like single photon emitters. Well, okay. Going back to this probability chart, there's actually a hard limit. The single probability, even when you have photon number resolving detectors, the single pair generation probability is capped at 25%. However, the way that you can hack this is by making a source that is pseudo-deterministic. And basically, what we say is that we kind of route a pump across like many. So this is a spatial multiplexing example. We route a source across many different channels and hook them up to. So let's say 5 different sources, and then we hook them up to uh, 5 different detectors, one for each source, and then we say, okay, in some unit time, one of those will click, and whichever one clicks will route that photon into the processing channel. So, and in that way, you can kind of hack the process a little bit, and you can get to like you can break this 25% probability limitation for limitation when you kind of just think about a single source. And for these kind of pseudo-deterministic sources, you actually need a large number. What you'll need is actually a large number of high performance components, including kind of links, kind of photon storage, either in a resonator or in a kind of delay line. And also you need fast switching to be able to process a detector signal and then like switch depending on which channel clicks to route that corresponding photon into a processing channel. So let's say a fast modulator. And this is where integrated photonics has a lot of potential to kind of enable kind of the scaling of these sources to help overcome the probabilistic nature. Yeah. And so that is it. And this is how it fits into the picture of integrated photonics. Now, we've talked a lot about sources, and in the section on probabilistic sources, we actually talked a lot about like we can't really think about where we want to operate the source or where it's best to operate the source without sometimes without thinking about the other end of the system, which is detection. And so now I'm going to start talking about single photon detectors, which is often what's used to provide nonlinearity in some of the ways that we perform logical operations on photonic qubits. And the first thing I want to highlight that about the difference between a classical photodetector, let's say an optical power meter or that kind of thing, compared to a single photon detector, is that a classical photodetector, what it does is that it turns an optical signal, in this case, like power, when it's incident on the detector, into an electrical current. And this way, and you can use a lot of there are a number of different materials, usually invisible. It's pretty standard. You use silicon. In telecom, you use indium gallium arsenide materials to do this. Whereas for single photon detectors, you're not actually looking at like the power because each photon has a well-defined energy. It's a pack, you can think about it as a packet of energy. So what you actually want is like a particle counter. So like if you've ever used a Geiger counter that kind of you wave around to look for radiation and it goes like click, 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 that's something that's more akin to a single photon detector. So in sense, what you have is that you have some kind of detector and then you have a single photon coming in, and every time it it is a photon is incident on a detector, you get a pulse, right? That we can think of as a click. Um, and what this pulse is in reality is like an electrical pulse, and then you can do some you can implement some circuits to do edge detection, and every time you detect the rising edge that is sharp, you say, okay, I have a photon here. And what's alluded to here when let's say like this by this like this particular pulse, which is a little bit higher, is that some detectors, you can actually distinguish between, let's say, single photons and multiple photons, but some detectors you can't. And the sensitivity, of course, for a single photon detector is much, much, much higher compared to a classical photodetector. We're usually operating in completely different power regimes for a classical photodetector at the if we're talking really, really high gain, you're still like in the femtowatt regime, whereas for single photon detector, you're generally looking at something like attawatts or 10 to the minus 18. Femtowatt is 10 to the minus 15, so 3 orders of magnitude lower. So for these kinds of detectors, So for these kinds of optical signals to electrical current detectors, you might be familiar with a number of uh detector figures of merit. But for these counting type of detectors, in general, the performance metrics that we care about are as follows. First, we care about efficiency. How often do we have lose a photon? So like when the photon is incident on your detector, how often does it not click? And what this impacts is kind of how many photons that you lose in your system. That can be factored into loss. You can group that into like loss per link or whatever. The other thing is how often does the detector click when there's no photon? That is dark count, and it can be kind of and that can be reduced much like classical noise by like let's say cooling the detector. Uh, the third thing is reset time. Like these pulses have a certain width, and then if the next photon arrives within the width of that pulse, then it's actually not going to be able to click again in general. And so that determines like how often, what's the highest rate the photons can arrive at. So if like every time a photon the detector clicks, you need to wait like, okay, I'm just gonna pull a number out here, like a millisecond for it to reset, then like your communication rate will be like locked to like a kilohertz, which is kind of untenable, right? So ideally you want the reset times to be short. And finally, there's an issue of timing jitter, which is that relative to when the photon arrives, when does this edge occur? And this timing jitter actually folds in a lot of different parameters. There's the jitter from the detector itself, and then there's also electronic jitter in terms of how you set up the amplification and its edge detection circuits that you use to kind of tag the edges. And this can be important for certain configurations where you're defining your qubits in terms of time bins, like you're defining, let's say, an early bin here and a late bin here, and you're trying to see like where they are relative to each other. Additionally, there are also other considerations such as photon number resolving, which we've alluded to previously, which will determine how often like how we operate our sources, and there's operating temperature considerations where there for these set of single photon detectors there are some that actually can operate at room temperature, some that can only be operated at cryogenic temperatures, which will become very apparent actually shortly. And then scalability, how once again how easy or hard it is to make arrays, and finally where actually are the wavelengths that the detectors are sensitive to. So in interest of time, I'll just like quickly blast through kind of how they work and kind of get to some like broad strokes metrics of how to think about these kinds of detectors. There are a number of existing single photon detector technologies. The first one I think like is the first one we can think about is a photomultiplier tube, which is like basically a vacuum tube. Um, which I think in general is not being used terribly much, just because like in terms when we were considering building integrated quantum communication nodes, partly because it's hard to miniaturize, etc. And then there are a whole slew of semiconductor-based ones, which basically consists of like making a normal photodiode in a certain way and then reverse biasing them so that it gives you clicks. Um, and then there's a third class, which is superconductors. And then there are two types, transition edge and nanowire detectors. In general, I think broadly speaking, most for a lot of applications, we tend to have converged towards using nanowire detectors. So um, so that's what we'll be focusing on. I'll give you one example of semiconductor detectors. But otherwise, we'll spend a little bit of time talking about nanowire detectors because these are kind of like the state of the art here. Let's for a single photon avalanche photodiode. In general, basically it operates like this, right? It's a it's a photodiode where when a photon is absorbed, there's an initial excitation, and then that initial excitation actually triggers an avalanche, and then So you get a large current and then it click and that gives you the click. And how you do it is basically you reverse bias kind of your detector at near breakdown. And the advantage of just of these kinds of detectors are that you can generally operate it at room temperature. If you think about like your normal photodiodes, yeah, you can just buy a silicon one off the shelf. You know, silicon photodetectors live in like, I don't know, like cameras and that kind of thing. And as you know, although it might not be as densely packed as the pixels in a camera, let's say, but you can generally make fairly large arrays of these. However, due to certain material interactions, oftentimes there can be after pulsing, which means after your initial large pulse that occurs from the single photon absorption of a single photon, there can be ripples that if you don't set your trigger levels correctly can kind of show up as artificial pulses. Now, if you don't set up your electronics correctly for other types of sources, you can also get this kind of effect. And basically the way to diagnose them is that you can look at correlations from, let's say, a photon pair source where you know definitely that you should only be seeing photon pairs arriving at one time bin. And then finally, there's some efficiency is rather limited in for the silicon-based. Well, efficiency is rather limited at non-visible wavelengths or wavelengths below 1 micron. So actually, it's fairly high, 70 to 80% for silicon, but actually ends up being quite low for indium gallium arsenide applications. So in general, for telecommunications photon wavelengths that we would like to operate networks at, these are not very popular. What is popular are superconductor based single photons detectors. And basically single photon, the main property that we are relying on for to detect photons with superconductors is that there is no DC resistance below some critical temperature. And there's some highly nonlinear transition. It's highly non. The resistance change is highly nonlinear near the transition edge, and basically you can kind of bias your superconducting device at a current just below where so for superconducting devices, there's a critical current above which the device stops being superconducting, and you kind of like initially bias your device like just below that point, and so that like when you absorb a photon, the current density kind of gets higher, and then it just like stops being superconducting, and then when it becomes resistive, a pulse will show up. And in interest of time, I'll skip through a bunch of these that kind of elaborate on this in more detail and just go to my summary slide, which is that in addition to kind of, and that these superconducting detectors, because you have to operate it in uh, as superconductors, and superconductors famously do not like room temperature all that much. You actually have to operate them cold, which for better or for worse, has not stopped many people from many groups from exploring integrating them onto let's say integrated photon in onto chips. So for a variety of applications, including kind of kind of reducing the heat load of like getting interfacing things with superconducting qubits that live at the bottom of the fridge, let's say, fridge readout, let's say. So we do have there are a bunch of waveguide integrated SNSPDs that people have come up with. Um, these materials, superconducting materials, the processes for depositing the material and also kind of the dimensions, the critical dimensions are actually quite stringent. So each wire is 100 nanometers. And if you have like mild constrictions in along the wire, so like if your dimensions changes a tiny bit, like you have roughness or something, that can affect kind of how well your detector performs. So in general, they tend like the demands on like sidewall roughness in kind of uh lithography resolution in order to make these devices tend to be more stringent than like what you would think of for general for other kind of for non-superconducting kind of electronic devices. But yeah, people have done it. It's a lot of effort, but you can do it. And they generally still don't necessarily perform quite as well as bulk detectors or non-integrated detectors. And there is some argument to be made that maybe you just want to keep the detectors separate because you don't want to cool down your whole photonic chip down to superconductor temp down to the temperatures that where superconductors can operate, because then like certain material properties start acting weird. Your electro-optic modulation can get a little weird. You can get higher photorefractive, let's say. These are all issues with lithium niobate. But nonetheless, it is a kind of active area of research. So in summary, superconducting nanowire detectors. So if you just remember two types of detectors that in general kind of people have been trying to put onto um onto integrated photonics chips, it integrated onto uh integrated photonics chips, I would just remember superconducting nanowire detectors and silicon single photon avalanche photodiodes. And I think they're quite different. For superconducting materials, your wavelength actually is relatively versatile. Usually what determines the operating wavelength is that you usually sandwich your photon in like a little cavity to kind of make sure that it gets absorbed in the active region. So it's actually depends on what wavelengths the cavity is designed for. The material itself actually can absorb photons across a very wide range of wavelengths, but it does have to be operate at cryogenic temperatures, and transition edge sensors especially can be photon number resolving, but you can also get photon number resolving SNSPDs too by applying a bunch of data analysis. And there are a lot of demos of waveguide integration. On the other hand, you have APDs, which have specific materials that you need to work with. Well, same for superconducting materials. It can be integrated on top of like materials for a number of materials, but then it has the advantage of operating at room temperature. So kind of the last question that I want to actually think about in the kind of a as a to cap off this section is, okay, I just wanted to kind of poll you guys and see like what you guys think in terms of the various trade-offs when it comes to using a a superconducting detector versus like one of those APDs, which have more restricted kind of wavelengths that are efficient at but can be room temperature. So I'll give us a bit of time. Yep, sorry, it had issues launching for a little bit. So I'll give a minute for the poll to run, and then well, yeah, I guess this is just a question for you to reflect on, I guess. It was supposed to be open-ended, but well, sorry about that. Okay. And I think, the story here is that kind of it's worth working on both in absence of like fundamental materials advances on superconductors, but in general, there isn't really something that kind of checks all the boxes yet necessarily. But for most laboratories, I think we tend towards using nanowire detectors just for their higher efficiency and kind of wavelength, higher efficiencies at telecom wavelengths that we like to operate at. So that brings us to kind of the end of this kind of quick section on light source, not so quick section on light sources and detectors. And hopefully, like by digging deep into all of these kind of individual elements and kind of thinking about what figures of merit are important for each kind of device that one might need in a integrated photonic integrated circuit that you want to place at quantum networking nodes. You have you kind of have a good framework for kind of starting to think about what you think makes a good integrated photonics platform to use for quantum networks. And so yeah, and here's just a list of the things that just a summary of all the things that we talked about. At the end of the day, what we want is a quantum network link. There are a lot of devices that we need to implement for them for a circuit that we want to put at quantum node networking nodes, and if we want to scale up a quantum network, ideally these would be cheap and can be manufactured scalably and leveraging kind of traditional semiconductor manufacturing technologies. And I'll turn it over to Marco for some concluding remarks.
I don't have very many. Shall I, is there a click or can we?
That's kind of just a concluding slide to
Yeah,
for everyone to kind of stare at and remember
I'm not
things.
sure if there's any questions. Let's see. There was a Q&A. There's four. Let's see what's there. Uh-huh. Continuous variable. Share slides. What was the metric for single photon source? Okay, you had three questions for you and one for me, sharing slides.
Okay, sharing slides is a you question,
Yeah.
because yeah. Uh I mean, I'll start with the first one to answer live, which is for CV. Would it be possible the question is, let's say we have a continuous variable system, would it be possible to encode intensity variation as a two-level system to generate noisy qubits? So that's kind of an interesting question, because it depends on what you mean by a continuous variable system. Um, if we are thinking about using single photons as your information carrier, then that doesn't it you can't really think of it as it's not intensity variation is not really a kind of observable of a single photon, a degree of freedom of a single photon that you can kind of define into like zeros or ones. That's because a single photon is a packet of energy. It has a well-defined energy. It doesn't really have, you can't really think about it as power or intensity. It's flux, right? So in that sense, it wouldn't really make sense to try to encode information in that degree of freedom because that's not a valid degree of freedom for a single photon. But in terms of continuous variables, as in encoding information into uh, a degree of freedom of light that can take on continuous values. So let's say like photon number is a discrete variable because you can only have one, two, three, right? But you can encode information in the quadratures of light or the position and momentum, whatever operators or whatever. You can use that for quantum information processing. In general, you would want to use this in a completely different way than the kind of two-level dual rail encoding that of like qubits. And I'm not actually sure whether you can just define logic levels um like you do, let's say with in like digital electronic circuits. Like you can't just, I'm not sure whether you can define logic levels and have it still function like a quantum computer, because you have to think about whether it holds up under change of bases and that kind of thing. Do you have any sense about this, Marco?
Sorry, trying to find. No, I think I honestly don't know. I don't have any better answer than you.
Yeah.
Uh, yeah.
Uh
First, I
yeah,
thought we'd like to modulate it, but it's maybe a little
yeah.
different. Maybe
Yeah.
you have the other slide or the other questions.
Yeah, I guess the answer to that particular question is um we both Marco and I both live in single photon land. And I think at least for me, I don't really have the expertise to comment on continuous variable and what kind of encodings, whether you can actually define logic levels or if you would even want to do that in the first place, and use it for quantum communication, computation, whatever. So that was answer live. Slides, yes. That will go through Brianna, I think. And then finally, and then the next thing. So the next question is that I would like, is what are the factors that decide if a pair of entangled photons have the same frequency? Right, so I think you're referring to the probabilistic single photon sources, which I will have to back up quite a lot. For probabilistic single photon sources, the main thing that determines whether it has a it has the pair of photons have the same frequency is, let's see, where's my helpful graph? Where's my helpful graph? Ah, yes, here. So for probabilistic single photon sources, right? What where you actually generate photon pairs is where you satisfy both mo energy and momentum conservation. So whenever these two curves, when you multiply these two, basically you get the probability of generating each point on this color plot reflects the probability of getting a pair of photon at that particular frequency combination. So let's say in this particular plot, if you look really closely at the scale bar, they're all centered on 0. If you pick the pump, um, if you pick the pump frequency so that it overlaps the phase matching at a point such that the highest point, the brightest spot is corresponds to the identical frequencies along here and here. That would give you the degenerate operating point. But what you were asking is entangled photons. So in this case, this pair of photons would not be spectrally entangled. They can be entangled in other ways, let's say in polarization. So what I said just now does hold. But then let's say if you look at this case, right, when they're spectrally entangled, actually when you multiply these two, even if they are overlapping in like a region where they are energy is conserved for degenerate wavelengths. So like let's say you want two 1550 nanometer photons. First of all, your pump needs to be centered on 775 and it needs to intersect your phase matching at 1550 on both sides. But without filtering, you're actually going to generate like non-degenerate photons other than at the point of degeneracy, because you have this line along the some frequency direction. So what it would determine is that you just like put a filter at 1550, and that's how you can get degenerate photons. Yeah, I hope. Yes. And then, okay. And then the next question is, are particle detectors, so single photon detectors, the only component that requires a refrigeration rig? I read that reducing noise was tied to operating at cryogenic temps and assumed that all electronic components were supercooled as well to reduce noise. Uh, Marco, would you like to comment on this? What other things need to be cooled?
Yeah, I mean the
Vacancy sensors.
single photon detectors for sure need uh uh like uh, low temperature. There's no way around it unless you operate at APD valence. Uh, so there's actually people who are doing frequency up conversion from telecom range to visible and then use silicon avalanche photodiodes that CJ was discussing. But still, best detectors are in superconducting ones. if you want to do photonic quantum computing, you don't need memory or photonic communication without memory, then that's true. You only need detectors at cryo. If you're using memories or qubits, like, like silicon vacancies, or if you're combining this with some transduction and using superconducting qubits, then those require superconductors as well. So yeah, that's kind of system level architecture question, I guess.
Yep. Yeah.
That's
Okay.
it. Yeah. Made it.
Yeah. Yeah. I think that's it. The remaining one is the slides. Oh, I missed one about metrics for a single photon source. I mean, in summary, it's kind of efficiency. Does it operate at the wavelength that you want it to be? And can you make a bunch of them, uh, and scale them? I think in general. There are a lot of other specifics that depends on your kind of your particular material platform and kind of whether you want to cheat and go for a probabilistic source or whether you want to work hard on your material and your controls to implement like a deterministic source. Yeah. And we'll talk about slides and get the slides to y'all at some point. Uh, yeah. And
Yeah.
I
Well,
sub
thank you
and that's
all.
it.
Thank you all, and yeah, let us know if via email or otherwise if there's any other questions or comments. Because there's going to be some questionnaire, right? Like a feedback, which we are looking for.
Yeah, yeah,
Yeah.
sure.
Not by us, by
Yeah.
thanks
Yes.
everybody.
Thank you. Um,
Yep. All right.
okay. All
All
right.
right. Have a good night.
Bye.
Bye, I guess. Yeah. Guess people signing
Uh,
off. To be honest, they're not sure.
All right, awesome, guys.
the
Thank you so much.
All right. See ya.
yeah, thank you for setting everything up, Brianna.
Of course. Have a good one.
Bye.